Hi everyone, welcome to Vedantu JEE English. I'm Diksha Kaushal, your chemistry master teacher. And students, today we are going to start with a very important chapter, that is aldehyde, ketones and carboxylic acids. So everybody in the chat box, am I visible? Am I audible to all of you? Everyone in the chat box, am I visible? Am I audible? Yes, everyone. I don't know if I'm visible to you or audible. God, that's a something ghosty thing happening here. Why I am not visible, guys? Is the screen visible to you all? Is the screen visible? Like where it is written Vedantu English? Is that visible to you? Is my voice audible to you? Is my hand visible to you? How much hours, Pita? Just give me a minute. I don't know why I am not visible. No idea on that. Just give me a second, students. Let me see why I am not visible to you guys. Okay, guys, just give me 2-3 minutes. I'll ask the team why I'm not visible. Ma'am, you're visible in the screen, ma'am. You are hiding behind the camera. Yeah, now am I audible? Sorry, now am I visible? Because to this OBS, I think I'm not visible because I can't see myself in the this OBS. What can be the issue, guys? What can be the issue? Yes, I think now I am visible, right? I don't know what happened. I think now I am visible to you, is it? I don't know, something like ghosty thing happened, right? Something though happened. Why I was not visible was I was not sure about that, right? But now I think I am completely visible to you, right? Okay, yes, ma'am. Please don't play Kanamuchi. Yeah, I think the God is playing with me. So sometimes the studio is not working and the studio issue is getting sorted in a week, right? Next week it will be sorted. I'll have my new studio and everything will be sorted. But yes, I don't know. I think I was like, am I a ghost or what? What just happened? Why I am not visible? Why the screen is visible? Right? I was standing here, but I can't see myself in the OBS camera. I was like, what is happening here? Right? Am I alive? Am I visible to other people? I was about to ask my parents, am I visible to you? Because the students are not able to see me. Okay. Hello, ma'am. I am your NEET student. Hello, 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 hello. Harshita, Sumati, Anirudh, Darshan, Gokul, Anil, Dhanshari. So, how many of you are JEE aspirants? Write it down in the chat box. How many hours will this session take? So, my target for today's session is to complete aldehyde and ketones, right, and some of the parts of carboxylic acid, because in the next session, right, we are going to take up the previous year questions, like a lot of questions I'll take up, and some of the questions I'm taking today as well, right? But like a big chunk of questions I'll take in the next session, but in that session I will not teach you theory. So today's session is mostly dedicated to theory, right? So in today's session we will talk about different reactions, right? How these reactions happen, what are the important reactions, naming reactions, the mechanisms of these reactions, and all of those things we are going to talk about in today's class. Okay guys, yes everybody, yes, yes students. I am 2025 aspirant, 2026 aspirant. Okay, perfect, perfect, perfect. Now, let us start the session without wasting any time, right? Okay, so are you all ready for the session? Are you all ready for the session? Everybody in the chat box. If you are ready for this session, then green hearts in the chat box for your Diksha ma'am. Okay, yes. And don't ask again and again, ma'am, how much time? Maybe around 2.5 to 3 hours it will take me to complete today's target. But you have to be fully focused here, right? Okay, guys, everybody, please take classes regularly. Yes, I'll take classes regularly. So guys, I'm going to take up the lecture on Tuesday, then on Friday. So I think that is a regular class only. Sunday, then Tuesday, then Friday. You have 3 classes here, right? So don't worry about that, right? Okay. Yes, previous year questions will be done in the next session, right? Today I'll take up around 10 to 15 previous year questions. In the next session, a lot of PYQs of your JEE, means and advance I will take up, right? But because before that we need to do the theory part, right? Otherwise questions will go out of your head, right? So let us start this, starting with the first thing, that is carboxylic acid, that is introduction to the carbonyl compounds. What is a carbonyl group? A carbonyl group is something which is like this. This is C double bond O. This is the carbonyl group. Now, if you talk about aldehyde ketones and carboxylic acid, there you see the carbonyl group. For example, if you talk about aldehyde, that is RCOH. Here you have this carbonyl group, right? If you talk about ketone, again you have this carbonyl group. If you talk about carboxylic acid, that is RC double bond OH. Here you have carbonyl group along with the hydroxyl group, right? So that is also a carbonyl compound. So in this chapter, we are going to talk about carbonyl compounds basically, right? So firstly, we will talk about aldehydes and ketones. They are somewhat similar. The preparation, the properties are somewhat similar. That is why we are going to study about aldehydes and ketones in one go, right? Okay. So as I told you, whatever we are going to study, firstly we are going to study about the preparation, then we are going to study about the chemical properties, then physical properties, right? These are the 3 things that is our target for today, right? So first thing, let us talk about the introduction to the carbonyl group. As you can see, this carbonyl group is introduced in so many things. These are all the acid derivatives. Carboxylic acid is COOH, right? If you talk about acid anhydride, right? If you have acid anhydride is formed by 2 carboxylic group. It's like this. It's like this. You have RCOOH and here you have RCOOH. This is the thing. Water will be eliminated from this side and you will have RC double bond O, C double bond O, and this is R. If I take it as R dash, this will be R dash. So this is called acid anhydride. That is why we say acid anhydride is the derivative of the carboxylic acid, right? So when you replace this, then students, we have Acyl halide, that is when you replace OH group with some halogen group, that is called acyl halide or acid halide, right? Then we have ester, when you replace this OH group with OR dash group, then we call it as ester. When you replace this OH group with NH3, that is called as amide. These are the derivatives of carboxylic acids, right? So these are all the compounds which has carbonyl compounds. First is aldehyde ketones, then you have carboxylic acid and its derivatives, right? So here we are going to talk about all of these things, right? Okay, so first thing is the preparation of the aldehyde and ketones. From different things we are going to talk about the preparation of aldehydes and ketones. First thing is preparation from hydrocarbons, right? If you talk about hydrocarbons, you have alkanes, you have alkynes, you have alkenes. Three things you have, right? In hydrocarbons, we have three things, no? So what are these three things? Everybody, hydrocarbons, we have three things. First is alkane, then you have alkene, then you have alkene, then you have alkyne, right? In alkane, you have single bond, right? Single bond, here you have double bond, and here you have triple bond, right? So these are the three things, alkene, alkene, and alkynes, right? Single bond, double bond, and triple bond, right? So if you talk about this thing here, it's very simple, right? Firstly, we will talk about how to prepare aldehyde or ketones from alkenes, then we will talk about from alkenes, then we will talk about from alkynes, right? Then we will jump to alcohols, acid derivatives, all of those things, right? So firstly, let us focus on how to prepare aldehyde or ketone from alkanes, right? So with alkane, what will happen? You will have controlled oxidation, right? Why I am saying controlled oxidation? For that, you need to know the pattern of oxidation, right? What is the pattern of oxidation, everybody? What is the pattern of oxidation? Anyone in the chat box? What is the pattern of oxidation? The pattern of oxidation, is this a high? This is the most important chapter of organic chemistry, right? You will see a lot of questions from this particular chapter. So yes, this is definitely a very high weighted chapter, right? So if we talk about this alkane, so firstly is we have alkane 2, the oxidation of alkane will lead to alcohol, right? Will lead to alcohol. Then the oxidation of alcohol will give us aldehydes, right? Or ketones. Then further oxidation will give us carboxylic acid, right? Why we are saying controlled oxidation? Because we want this alkane to convert into aldehyde and ketone. We don't want this alkane to get converted to carboxylic acid. That is why we need to use specific reagents for this controlled oxidation, and that specific reagent is this one, where we are going to use molybdenum oxide, right? Molybdenum oxide we are going to use. Molybdenum oxide at high pressure and high temperature, right? Temperature is 200 degrees Celsius, a very high temperature, and a very high pressure, that is 100 atmospheric pressure, right? With this, if we react this with oxygen, if we, for example, I am reacting methane with oxygen, with the same number of carbon, it will form the aldehyde, right? So here what we are going to say, that takes place in presence of suitable catalyst at high temperature and high pressure, and with the same number of carbon, you are going to form the aldehydes, right? Here aldehydes will be formed because it is going to react on the terminal carbon, right? So that is why aldehyde will be formed here. Next is from alkene, right? From alkenes, the first part is ozonolysis. Now, ozonolysis of alkenes we have already done, right, in hydrocarbons, but I will again teach you the ozonolysis. Ma'am, mild and strong. Yes, it depends. Now, this is a selective oxidation. This is a very mild oxidizing agent. This is not even an oxidizing agent. You can say we have selectively introduced this catalyst, this reagent at high temperature pressure, right? Okay. Now, by ozonolysis of alkene. Now, with ozonolysis of alkene, it's a very simple thing. You will have this double bond, right? Wherever you will see double bond, You just need to break that double bond and convert it into double bond O. That's it. That is your ozonolysis of alkenes, right? So there are two types of ozonolysis. One is reductive, one is oxidative ozonolysis, right? So in reductive and in oxidative, what happens? Let us see, right? If you talk about the reductive ozonolysis, if I talk about a compound that is CH3, CH2, double bond, CH2, CH3. This is my compound. One I am doing reductive, other I am doing oxidative. If I talk about the reductive ozonolysis, that is RO, reductive ozonolysis, in that case, you just need to break this double bond, right, and apply here and attach here double bond O, right? So that will be the answer. So break this bond and you will have double bond O and this will become H, right? And here also you do the same thing. Break this double bond, right? 2, 3, 4, 2, 3. This, it should be hydrogen, one hydrogen. It should also be one hydrogen, right? So break this bond and you will have, this is CH3, this is CH3, wait a minute, this is CH3, this is C double bond O and this is H. So this becomes your other compound, right? So break this bond and attach double bond O, break this bond and attach double bond O, that becomes your answer. Now, this is reductive and this is oxidative, right? So here, in this case, wait a minute, let me see one thing. Let me show you one thing here. Here, two products will be formed, right? One is this one, other is this one. So it will be again, if I change it to, if you want to change it, you can do it. You can make it CH, CH2, CH3, right? I think now this will be better for you to understand. Break this bond, attach double bond O. Break this bond, attach double bond O here. So it will become C double bond O, H. Rest of it is CH2, CH3. It is CH2 and this is CH3. Right? CH2, CH3. Right? Everybody? Now, same thing as it is, I am going to write in oxidative ozonolysis as well. Right? So write the same things. This is CH3, C double bond O. This is H plus you have C double bond O, this is H, this is CH2, this is CH3. Now in oxidative ozonolysis, you will further replace the hydrogen that is attached to the carbonyl compound to OH. Replace this hydrogen to OH, replace this hydrogen to OH. This will be the answer for oxidative ozonolysis. So basically two kind of ozonolysis you have, reductive and you have oxidative. If you talk about reductive, they will use Zn, O3. O3 to definitely will be there because it is ozonolysis, right? Then they will use Zn here, right? If they use H2O2 with O3, then that is oxidative ozonolysis, right? Understood? Right? Everybody in the chat box, that is also applicable if they ask you that you are using KMNO4 or K2Cr2O7 in a basic medium or in a neutral medium, then the answer will be same as reductive ozonolysis. If they tell you that you are heating it, it is in the acidic medium, the oxidizing power of that K2Cr2O7 or KMNO4 will increase and they will further oxidize this hydrogen to OH, this hydrogen to OH. Is this thing clear to everybody or not? What is ozonolysis? How to do reductive? How to do oxidative ozonolysis? Whatever is given to you, you just need to break this bond and attach double bond O here. If they ask you further oxidation, replace this hydrogen with OH, replace this hydrogen with OH. Everybody in the chat box, is that clear to you or not? Is that clear or not? Now let us see this. This reaction is used to determine the position of the double bond. How the position of the double bond is determined here. Now if you see this, if I say that these two are the products of ozonolysis, right? If you say that these two are the products of ozonolysis, how you can make the reactant out of it? This is also another question that can be asked. If I am giving you just two products, you need to tell me what is the reactant for the ozonolysis process, right? For example, they are giving you CH3, C double bond O, CH3, one is acetone, other is CHO, CH2, CH3. Now you need to tell me what will be the reactant if I say they are going under reductive ozonolysis or simple ozonolysis. Even if they ask you just ozonolysis, that is reductive only. If they have specifically mentioned oxidative, then you need to give the answer for oxidative, right? Yes. Yes, in oxidative ozonolysis, you will get carboxylic acids. Yes, definitely. Right. So now, as you can see here, the reactant will be, you just need to break these two things. For example, this is CHO. You can also write it as C double bond O and this is H, right? Or you can also write it as C double bond O and this is H. So now what you need to do, you just need to eliminate this O, right? You just need to eliminate this oxygen and attach these two carbons and it will become your reactant. So it will be C, this is CH3, this is CH3, this is CH3, this is CH3, right? And this is double bond, this is C, H, CH2 and this is CH3. That will become the reactant. This is another kind of reaction question that they can ask you related to ozonolysis. They can give you the products, they can ask you what will be the reactant for the ozonolysis process, right? Okay guys, everybody in the chat box. Okay, perfect. Now let us see further what you can do. Now this is the process of ozonolysis. I have already told you the trick, but if you ask me the mechanism, what will happen? So basically this O3 molecule, right, that will break these two bonds, right, and it will get attached here, right, like a hut, like you make a hut like this, no? It's like a house, right? So someone like O3 has come in the life of this alkene. Now they will break this double bond, right, and they will make their own house, right? So after that, what will happen? House has been formed. Now the house will also break, right? The house will, it's like you are getting into a relationship, you are making a house and then there is breakup, then the house is also getting break, right? So now what will happen further? This house is going to break, right? And in this process, what will happen? These two bonds will break, these two bonds will break. This oxygen will go out as it is, as water, right? But this oxygen will stay as double bond, this oxygen will stay as double bond here, right? So that is the proper mechanism. But I have told you the trick here, that just break the double bond, just break this double bond and attach double bond over here. That's it. Okay, that is the trick. But how it was done? It's like this, right? So similarly for this compound, break this double bond and it will be RCH double bond O and this is R, right? And here this will break. And here you have 1, 2, here the hydrogen should not be present here, right? It is C double bond O, this is H and this is H. These two things will be formed here, right? So you just need to break the double bond there, right? Okay. Next is again one more reaction, that is second. First was ozonolysis, second is oxidation, right? So this is same as ozonolysis only, right? So let me tell you what is the trick to answer these questions, right? So as I told you, acidified KMnO4 will give the same answer as oxidative ozonolysis. It will give the same answer as oxidative ozonolysis, right? But if you have dilute KMnO4, right, that will give you same answer as reductive ozonolysis, right? So here strong oxidizing agents like K2CR2O7, hot alkaline or acidified, even if they use, very important, if they heat the KMnO4 or they acidify the KMnO4, right, or you have simple K2CR2O7, they will give the same answer as oxidative ozonolysis. That means you need to break this bond and attach double bond over here, attach double bond over here, right? Then here you will not have any hydrogen. Wait, let me show you on next page, right? So basically this is the question, right? This is the question, right? Now they are asking you what is the answer for hot alkaline KMnO4 or K2SCR2O7 or acidified KMnO4. The answer will be same as oxidative ozonolysis. Just break this bond here and what you will get. Break this bond here, you will get this thing, you will get this thing, you will get this thing. This is your compound. You just need to break this bond, break this bond. Rest of the things are same, right? You will attach double bond over here, you will attach double bond over here. Now here you don't have any hydrogen. It is double bond O, CH3 and this full ring here, right? This full chain here, right? So there is no hydrogen. But in this case you have one hydrogen. That is why further it will convert this hydrogen into OH. It will convert this hydrogen into OH. That is why what you will say, that what you will have in the end, this is COOH and this is CH3, this is double bond O. This will be the answer in the end, right? This will be the answer in the end, right everybody? This will be the answer. So if we talk about the next question here, you have something like this. Now what will happen? You have something like this, right? Now what will happen? Right, so similarly do the same thing. Break this double bond and attach double bond O here. So it will be, the answer will be, this was the answer. This was the question. You just need to break this double bond here. Break this double bond and attach double bond O here. And attach double bond O here. That is going to be your correct answer, right? Now here you don't have any hydrogen because to this carbon the 4 bonds are completed. To this carbon also the 4 bonds are completed. That is why there is no hydrogen. That is why we say that here hydrogen is not getting converted to OH because there is no hydrogen that is directly attached. So this will be the correct answer. Okay guys, now this will be the correct answer. Everybody in the chat box, is that clear or not? Yes, I'll definitely teach. Don't worry about that. I'll definitely teach, but please right now focus on this thing, right? Okay, it totally depends on your response, right? What response you are giving, right? Depends on that what I will teach. Okay, guys? Okay. Now, students, tell me, is this thing clear to all of you or not? Is this thing clear to all of you or not? Yes. Is this thing clear to all of you or not? Clear? Oh? Very good. Now, third method here is Wacker's process, right? So in this Wacker's process, very direct question will be asked to you. Here you have a alkene that is converted to aldehyde on ketones, but the important part is if you have ethene, then you will have the formation of aldehydes because it is going to attach a double bond O here. This double bond will be converted to single bond and one double bond O will be attached here, right? But if you talk about the other alkenes, right? For example, if I talk about propene, if I talk about butene, right? Other alkenes except for ethene, then this will not attach double bond O. Rather, the center, the carbon that is in the center, that means the terminal carbon will not attach double bond O. It will only attach double bond O in case of ethene, right? If you talk about this case, here double bond O will be attached here and it will be converted to single bond, right? This will be the answer here, right everybody? Now tell me one thing. If I give you one question here, if you have CH3, CH2, double bond CH2, right? This is CH2, this is CH3. Now what will be the answer? If you talk about the Wacker's process, what will be the answer? In Wacker's process, the answer will be this bond will break, right? And what will happen? This is CH3, right? This is CH3. Wait a minute. This is CH3. This is CH2. This is CH2. This is CH2. This bond will break, right? And one hydrogen will shift here. So this will be CH3. And this hydrogen has been shifted. That is why it will be double bond O in this case. 2, 3, 4. So it will be CH2 only. One hydrogen has been shifted here. So it will be like this. Ketone will be formed, right? Ketone will be formed. So always remember one thing, that for Wacker's process, alkene, or you can directly say ethene will form aldehydes. Ethene will form aldehydes. If you talk about any other thing, if you talk about any other alkene, that will form ketone. Very, very important. Ethene will form aldehyde. All the other things will form ketone. Right? Okay. Very good. Yes. Now, let us see the next example. Yeah, this I have told you. Now, what is going to be the reagent here? Right? So, here you will use PdCl2 and CuCl2, right, in the presence of air. Right? So, basically, this reaction is going to happen with air, but these should be the catalyst. Alkenes can directly be oxidized to corresponding aldehyde compounds by treating them with solution of PdCl2 containing a catalytic amount of CuCl2 in presence of air or air of O2, except ethene, higher alkenes will give ketone. Right? Okay, guys. Now, next is from alkenes, the fourth process is oxo process. Right? Fourth process is oxo process. Here what we are going to use? We are going to use water gas here. What is this? Carbon monoxide plus H2, that is called water gas. In the presence of this coordination compound, right, and pressure and heat, right, what will happen? You will have a alkene, but here in this case, this double bond will break and one more CHO group will be attached here. Right, one CHO group can be attached here or it can be attached here. So, two products will be formed here, right? So, answer will be this double bond will break, right? And here you will have the attachment of CHO, right? What is the difference between Wacker's and oxo process? Here you had the attachment of double bond O, right? To this position you are attaching just double bond O. To this position you are attaching this double bond O, right? You're breaking the double bond and you're attaching double bond O, right, to one position, right? But here what you are doing in oxo process, you are attaching CHO group here, right? So CHO group from this thing, CHO group will be attached either on this position or on this position, right? In these two positions, CHO group will be attached. That is called oxo process, right? There is no major minor group here. Both are formed here, right? A mixture of this product is, first is this one, right? Second is this one. These two things are formed here. That this double bond will break when CHO is attached here. This is formed. When CHO is attached here, this product is formed, right, guys? Okay. Okay, what is the difference between Wacker's? What is oxo process? What is oxidation? And what is ozonolysis? These are the reactions when you want to prepare aldehyde or ketones from alkenes. So, is this all the things clear to you or not? Are all the things clear to you all or not? We have done 4 processes till now, right? We have done 4 processes till now, right? From alkenes, one is ozonolysis. There we saw oxidative and reductive ozonolysis. Then we saw using KMNO4, K2Cr2O7. That will give the same answer as oxidative ozonolysis. Then we saw what is Wacker's process and then oxo process. These are the 4 preparation steps, right? Now, next we have is Next we have is dehydration of alkynes, right? That is very, very, very important, very important question, right? So here, why this is important? Because of this thing called tautomerism. Now, let me take an example here. Let us take an example of, here they have given you CH triple bond CH. Let's take this example only, right? Let us see what is going to happen. CH triple bond CH, and let us see the reactant, the reagents that they will be using. Hydration with H2SO4, dilute H2SO4, along with mercuric sulfate. That means you will have 1% of Hg2 positive ions in the solution, right? So now let us see what is going to happen, right? So this is the thing, you are attacking it, you are attaching H positive and OH negative here, right? So what you're going to do, you're going to do the same thing that you did in alkenes, right? Just break this bond, break this one pi bond. So this is CH, this is double bond, this is CH. When you break this one pi bond, what will happen? One hydrogen, H positive is attached to one side, one OH negative is attached to one side. Now, next is what you will have. Next is, isn't it enol? Isn't it enol? You have double bond, then you have ol. So this is enol. So there will be keto-enol tautomerism here. So how to answer keto-enol tautomerism? Let us see here. Right, how to answer, how to convert enol form to keto form, right? So what you need to do, this double bond will be shifted here. You need to say this is 1, this is 2, this is 3, right? So double bond is shifted from 2 to 3 to 1 to 2. Here the double bond is shifted. This hydrogen is shifted here. So it will be, wait a minute, this hydrogen, this double bond is shifted here, right? And this is keto form will be, aldehyde form will be formed here, right? So this hydrogen is shifted here on this side, yeah. Hydrogen is shifted from first position to third position, so that is CH3, right? Rest of the things will remain same. Here you will have the formation of aldehyde. In case of ethene, you will have the formation of aldehyde. Right, if you talk about the formation of ketone, let us see one more process. Right, so this is called the keto form. This is called the keto form. So we'll talk about one more reaction here. If you talk about, you have CH3, CH, triple bond CH. Then you have CH3. 1, 2, 3, 4. There should be no hydrogen here. There should be no hydrogen here. So this is C, this is C. Now you need to tell me what will be the answer if you do the hydration, right? If you do the hydration, what will happen? If you do the hydration, what will happen? This bond is going to break here. This bond will break, right? To one thing, you will have the attachment of, this is C, this is double bond, this is C, this is CH3. To one side, you will have the attachment of hydrogen. To other side, you will have the attachment of OH, right? Then this is your enol form. This is your enol form. If you talk about to convert it, it is 1, it is 2, it is 3. Now, the double bond is shifted, right? What you need to see here, the double bond is shifted from 1 to 2 position. This is 2 to 3, this is C and this is CH3. And here you have O. Double bond is shifted from 2-3 position to 1-2 position. So it will be double bond O here, right? It is double bond O here, or you can just directly write it like this. This is double bond O here. After that, this hydrogen is shifted here. So already you have one hydrogen, then you will have two hydrogen. This is the keto form. This is the ketone that will be formed here after tautomerism, right? This is tautomerism. Tautomerism. After tautomerism, this thing will be formed here. Right, guys? This thing will be formed here. Everybody in the chat box, tell me, is that clear or not? Which second example, Pavitra, you are talking about? Which second example, Pavitra? Now, that was about the, what is that called? This is called Kirchhoff's reaction. Kirchhoff's reaction, right? Very, very important reaction, right? Why this is important? This is because of the tautomerism step, right? Now, here we were talking about the symmetrical alkenes. What if they give you unsymmetrical alkenes? Ma'am, what are these unsymmetrical alkenes? Unsymmetrical alkynes, for example, they give you CH3, CH, C triple bond C, and this is, yeah, CH. Now, what about this thing? What if they give you this thing? Now, what will be the answer? Now, what you need to see, the bond will shift either on this side or on this side. There are two cases that can be formed. This is CH3, C, double bond CH. If the electrons of this pi bond are shifted to this side, so it will be negative here, positive here. In that case, or it is shifted to this side, it will be CH3, C double bond CH. It is shifted to this side. Electrons are shifted here, so there will be positive on this side. Right? Now, what you need to see here, very important thing, right? So here, if it is shifted like this, you will have the attachment of hydrogen over here, right? So hydrogen is attached here, right? So you will have one hydrogen here. But in this side, to this negative, hydrogen is attached here. Now tell me which carbocation is more stable, this one or this one? This is A and this is B. Which carbocation is more stable? Which carbocation is more stable? Everybody in the chat box, which is more stable? To this, you have the direct attachment of, this alkyl group, right? Here you don't have the direct attachment of alkyl group. That is why it is going to give you electrons. It is going to donate the electrons, right? Here there will be plus I effect. Because of that plus I effect, there will be donation of electrons. That is why, can I say that this B will be more stable, right? Can I say that this B will be more stable? Because here you don't have direct attachment of the electron donating group. But here you have the direct attachment of the electron donating group. So can I say that this B is more stable? That is why this thing will be eliminated and this will be selected, right? Now after this, after selecting this, further what you will do? You will attach OH negative here. So it will be CH3, COH. This is CH2, right? Okay. And here you will have this double bond. Now this is your enol form. Rest of the things will be same. Rest of the things will be same. After this, what you are going to do? You are going to convert it into the keto form. So this is 1, 2, 3. This is 1, this is 2, this is 3. Right? Make it as it is here. This is CH3, C, CH2, and this is O. Right? So here, this double bond is shifted to 1, 2 position. So it is double bond here. Right? And this hydrogen is shifted to this position, third position. So it is CH3. Right? Okay. And hence you will have the formation of this ketone. You will have the formation of this ketone. And this is by tautomerism. Tautomerism. Right? Okay. Okay. Yes, everybody. Is there any problem till now? Is there any problem till now? This is same thing they have told you. And here you have the formation of this ketone. Right? This I have explained you in detail why it is so. This thing I have explained you in detail. Right? Same reactant I have used. And in detail I have told you why we have chosen this over this. Right? Then why enol to tautomerism is formed here. Right? Okay, everybody. Next is for doing the hydroboration-oxidation. So for hydroboration-oxidation, I am going to give you a direct trick here, right? You are going to use anti-Markovnikov rule. The answer is anti-Markovnikov rule. Markovnikov rule without rearrangement. Without any rearrangement, right? There is no carbocation, nothing is formed here, right? Directly use anti-Markovnikov rule without any rearrangement, right? So break this pi bond, right? Understand one thing, you will make CHO group where? Okay, so wait a minute, let me show you the full-fledged answer here, right? So this is RC triple bond CH, okay? So let me write it here, RC triple bond CH. Do the same thing. Firstly, use anti-Markovnikov rule, right? So we know that here also we are using H positive and OH negative, right? Hydration we are doing, right? So this H positive is attached where and OH negative is attached where. That is the first question to be answered, right? So here always remember that the negative part is attached to the more or less. What is anti-Markovnikov? What is anti-Markovnikov? Can you explain what is anti-Markovnikov? Arey, what is anti-Markovnikov? Rich to rich, poor to poor, right? So negative, which has more electron density, will go to those hydrogens, that carbon which has more number of hydrogens, right? So negative part, that is OH negative, is attached to that carbon which has more number of hydrogens. More number of hydrogens are present in this case, so answer will be RC double bond. This is CH, and here you will have OH, and here you will have H. Is that clear? Is that clear to everybody? You don't need to make the carbocation here. In acidic hydration, here I made one carbocation. Then I saw which carbocation is more stable. Right? There are two things. One is acidic hydration in presence of Hg2 positive ions. I did the same thing. I'll break the double bond, then I will attach H positive and OH negative. But in case of acidic hydration in presence of Hg2 positive, I am going to break this bond and I am going to form the carbocation. Then I am going to see which is more stable. Right? This was more stable. That is why I will proceed with this product. Right? But if I talk about hydroboration-oxidation, here the things are very, very different, right? Why? I am not going to think about any cation or anything like that. I'll just simply say that I'll attach my negative part according to anti-Markovnikov rules. That means negative to more number of hydrogen. What is this negative part? That is OH negative, right? So OH negative is to more number of hydrogen. That is why it is attached here and this side is formed. Now this is called the enol form, isn't it? This is called the enol form. Then I'll do the same thing. This is 1, 2 and 3, right? Then what I'll do, I'll just convert it into, this is R, this is C, C, H, right? R, C, H. This is double bond O. Here this OH is converted to double bond O. And this hydrogen is shifted here and this becomes CH2, right? So that is the answer that is formed here, and this is called aldehyde. This is called aldehyde is formed here, right? Okay, hi Tanuja, yes. Yes, definitely you can get if you prepare well, right? If you prepare well. Now, is this thing clear to everybody or not? Is this thing how we got from this position to this position, right? I have explained you in detail. Firstly, you are going to use anti-Markovnikov rule here, then just tautomerism, right? Next process is tautomerism. Now, students, tell me, is that clear to everybody or not? Is that clear to everybody or not? Everyone in the chat box, tell me, is that clear or not? Is that clear or not? Is that clear or not? Yes, everyone. Yes, everyone. Is that clear or not? Not enol, no ma'am. It is enol, no ma'am. Yes. You can say that, yes, it is enol, right? So yes, enol you can say. Wait a minute. Usually we call it as keto-enol tautomerism, right? But definitely this is enol, and here aldehyde is formed after that, right? Here this is enol only, no, this is ene and this is ol. This is from enol, aldehyde is formed. So it will be not keto-enol tautomerism, it will be aldehyde-enol tautomerism, right? Okay. Okay guys, now next thing is, I can't see your energies in the chat box. Why your energies are so low? Huh? Why your energies are so low? So, so tensed, right? Don't worry, be happy, right? Be happy, don't be so scared, right? If you learn something in such a stressful manner, then everything will be vanished out of your head, right? So, be more passionate about what you are learning, right? Be more excited, be more happy, be more, that I will do that, right? So I have to do that. I'll sit here for how many hours ma'am is teaching. I'll sit here and I will do everything that ma'am is saying, right? So have that energy, right? Don't be a very boring person, right? So in studies also, if you are studying like this, that I want to study this and that, the study will automatically become very, very boring for you, right? So now let us talk about geminal dihalides, right? What is geminal dihalides and how they are formed? Right, from geminal dihalides, right, if you want to make the ketones and aldehyde, what you will do? Firstly, geminal means on that position only you have two halogens. On one carbon, when you have two halogens, that is called geminal. Okay, so on one position you have two halogens, that is called geminal dihalide. Right, so when you use KOH here, definitely KOH in aqueous solution, that is going to replace halogen with OH, so that is going to replace the Cl and Cl with OH and OH here. Now a carbon cannot have two OH groups, right? That is why what will happen here, this OH negative will be eliminated from this side, and to this point, wait a minute, to this point you will have this H here, right? You will have this H here. Now this H positive will be eliminated, this negative will jump here, right? Or you can say this bond will jump here, and hence you will have the formation of CH double bond O, that is acetaldehyde. The CHO group will be formed here. Similarly, with another case, this Cl and Cl will be replaced by two OH, right? One carbon cannot handle two OH, that is why OH is eliminated to this side. And here what you will have, wait a minute, and here what you will have, this hydrogen will be eliminated like this, right? Here you will have this hydrogen, right? And here it will be eliminated, right? It will be eliminated, right? And here this double bond, this bond will be shifted to this side, and hence you will have CH3, C double bond, CH3. That will be formed here. That is going to be the answer. Okay, that will be formed here. Yes, everybody, that will be formed here. Understood? This is from geminal dihalides. This is from geminal dihalides it is formed. Right? Okay. Okay. Ma'am, please explain tautomerism. Tautomerism is very simple. For example, you have double bond O and this is OH. Right? Then what you are going to do? You are going to just write it here. This double bond is shifted to this OH position. Right? So what will happen? This double bond is shifted to this oxygen and this hydrogen is shifted to this one. This is formed. This is keto and this is enol. Right? So this is keto-enol tautomerism. Right? Okay. Next is from alcohols. So yes, everyone, let us do it from alcohols. What will be formed here? Right? From alcohols, what will be formed here? So if you talk about the alcohols, if you talk about the oxidation of alcohols, so answer is you will have different things will be formed. If you talk about, firstly, we need to understand the mild and strong oxidizing agents here. Mild oxidizing agents are PCC, that is pyridinium chlorochromate. Right, pyridinium chlorochromate is basically, this is pyridinium, this is pyridine, right? To this pyridine, you will have the attachment of this H, so it will be H, this is positive. Then you will have Cl negative, this is pyridinium. Chlorochromate is CrO3 here, right? So pyridinium chlorochromate, right? Then you have pyridinium dichromate. That is when you have to this pyridine, you have the attachment of CrO3, right? That is called pyridinium dichromate, right? Then you have Collins reagent, that is also weak oxidizing agent. Here you will have chromium 4 oxide with pyridine complex, right? Then if you have CrO3 in a neutral medium, that is also a mild oxidizing agent. So these are the list of, if you see anywhere PCC, PDC, chromium 4 oxide in pyridine complex, or you see CrO3 in neutral medium, that is a mild oxidizing agent. But if you talk about in a neutral medium means if you talk about acetone, right, in a neutral medium. If you talk about strong oxidizing agent, we firstly is Jones reagent, a very, very important reagent. Here CrO3 in presence of sulfuric acid, H2SO4 with sulfuric acid and water, it is going to be a very strong oxidizing agent, right? It is going to be a very strong oxidizing agent. KMNO4 itself is a very strong, and K2Cr2O7 is also a very strong oxidizing agent, right? So now we will see how they are going to affect and how they are going to make different things here. So as I told you that from alcohols how aldehyde ketones, carboxylic acids are formed. Let us see this here only, right? So you have three kind of alcohols. One is primary. Primary means you have CH3, CH2OH. Then you have secondary, that is CH3, COH, and this is CH3. This is secondary. If you talk about tertiary, that is CH3 here also, CH3 here also. This we have done in alcohol as well. Alcohol, phenols and esters, we have done this thing, right? So this is primary, this is primary, this is secondary, and this is tertiary, right? So you have three things here. Now see one thing, if you talk about the primary one, so this is CH3, right? Now, mild oxidizing agent, this is strong. With mild, this OH is converted to this C, this will be one double bond O, and this is hydrogen. That means this is converted to aldehyde. So it will be basically like this. It is basically like this. This is one hydrogen here, this is one hydrogen here, this is OH. So this OH is converted to double bond O, right? And this is the hydrogen here, right? So basically that is why you have this double bond and this hydrogen is left behind and you have aldehyde in the first phase. Then if you are further oxidizing it using strong oxidizing agent, this hydrogen is further converted to OH. The CH3 double bond O, this is OH, right? CH3, C double bond O, OH. Now what about this thing? What about this thing? Here OH is converted to, this is CH3, this is C double bond O, and this is CH3, right? This OH is converted to this double bond, right? And hence you have the formation of ketone. Further, there is no hydrogen on this carbonyl carbon. That is why further there will be no oxidation, right? If you talk about tertiary, here you can't replace this OH with double bond O because carbon cannot be pentavalent. It cannot be like this. This will be CH3, this will be CH3, this will be CH3 and double bond O. In that case, carbon will be pentavalent, which is not possible. That is why with tertiary, oxidation will not happen only, right? And this is aldehyde, this is aldehyde, this is carboxylic acid. From here you can see that how from alcohols you can form carboxylic acid, alcohols and ketones by using different oxidizing agents. Here we are talking about mild oxidizing agents. Here we are talking about all the mild oxidizing agents. Here we are talking about strong oxidizing agents. And I have given you ample of examples related to what is mild and what is strong oxidizing agent, right? Okay, we have done two things. Firstly, we have differentiated mild and strong oxidizing agents, right? If you see this thing anywhere, then 1 degree will be converted to aldehyde, 2 degree to ketone. But if you see This thing anywhere, strong oxidizing agents like Jones reagent, 1 degree is converted to carboxylic, but 2 degrees converted to ketone only. 3 degree has nothing to do with, you have mild or strong oxidizing agents, 3 degrees chill only, right? Then we have this, so we have done oxidation of primary alcohol. This is weak oxidizing agent, right? Again, we have, this is a weak oxidizing agent, right? Then if you talk about, now they are saying with weak oxidizing agent, this method is suitable for volatile alcohols of industrial application. Alcohol vapors are passed over heavy metals. Wait a minute, this is by dehydrogenation of alcohols. Okay, if you, they're saying that if you pass this heavy metal like Ag and Cu, for the copper is very famous. In that case, primary is converted to mild only, that is aldehyde. Secondary is converted to mild only. With 1 degree and 2 degree, they will behave as a mild oxidizing agent only. This copper or silver at a very high pressure, at a very high temperature, right? So here 1 degree is converted to aldehyde, 2 degree is converted to ketone only. But 3 degree is not converted, right, to anything but to alkene. This is very, very, very important, right? This is very, very, very important, that how 3 degrees converted to alkene. Okay? Yes, everybody? Right? So 1 degree to aldehyde, 2 degree to ketone, but 3 degree is converted to alkene. Right? 3 degree to alkene. If you want me to show how it is converted to alkene, let us see the example here. This is CH3, CH3. This is CH3. I'll write it like this, and this is OH. Right? And you are adding, and you are reacting this with copper, right, at 300 degrees Celsius. Copper at 300 degrees Celsius, right? The answer will be, this is C, this is CH3, this is CH3, but OH will be eliminated here, H will be eliminated, H will be eliminated, this double bond will be shifted here. The answer will be double bond CH2. That is going to be the answer. That is alkene, right? That is alkene is formed here, right? Okay. Definitely activation energy will vary, right? Okay, guys. Next thing is vicinal diols. Now we talked about simple 1 degree, 2 degree, 3 degree alcohols. Now let us talk about vicinal. Now, geminal means when on the same carbon you have two groups. Vicinal means when on two different carbons, opposite, not opposite, adjacent carbons, you have two OH or halogen group. Because here they are talking about diols, that means two OH groups should be present on the adjacent carbon, right? And here, to correct it, it will be like this. Wait a minute. This is a double bond here, and here also there will be one double bond, right? Okay. Now, what you will have, this is benzene, this is COH, this is COH, this is CH2, CH3. What will happen? You will break this bond, right? You will break this bond, right? And what will happen? This OH is here converted to double bond O. This OH here is converted to double bond O, right? This is converted to break this bond, this is converted to double bond O. Break this bond, this is converted to double bond O. This is how you will have from vicinal alcohol, you will have different aldehydes or ketones depending upon what is the reagent, how many substituents it has, right? Now, vicinal diols are cleaved by, what you will use here, they are cleaved by HiO4 to yield aldehydes ketones depending upon the number of suitable reagents, suitable substituents of carbon atom bearing hydroxyl group, right? So now you can see this. I'll give you one example here. If you have C, this is OH, this is again OH, this is C, CH3, CH2, CH3, right? And this is CH2, CH3. Now what will be the answer? What will be the answer? Break this bond, right? Break this bond. Don't feel that this is how the bond will break, right? This is just a way of showing you that this bond we are breaking, just a trick I am giving you. Otherwise, bond will always break like this. Electrons will be shifted, right? So as we are not doing the mechanism, I am directly giving you the tricks here. So break this bond and convert this OH to double bond, OH to double bond O. So it will be CH3, CH2, C double bond O, and this is CH3, right? And this is CH3 plus this is again CH3, CH2, and this is again C double bond O, and this is H, right? So these two things are formed here, right? Okay guys, everybody in the chat box, is that clear or not? Is that clear or not? So this thing will be formed here, right? Okay. Next is from dry distillation of calcium salts. Now we will do how to convert from carboxylic acid salts, right? How to make aldehyde and ketones from carboxylic acid salts. Yes. Now let us see that this is a carboxylic acid salt of calcium, right? So calcium, as it has 2 positive, Ca2 positive, that is why by cross multiplication it has 2 ions of HCO, right? So simply what you need to do, you just need to heat it, and what will be formed with the same number of carbons, aldehyde is formed, right? With the same number of carbon, ketone is formed, right? How this is formed, let us see that. If you talk about, if inside you have HCOO, in that case aldehyde is formed. But if inside you have RCOO, in that case RC double bond O, R is formed. That is why symmetrical ketone is formed here. Symmetrical ketone is formed. If inside in this bracket you have HCOO, then you will have the formation of methanol, right? If you have RCO, then you have the formation of symmetrical ketones. But for the unsymmetrical ketones, you need to have 2 different carboxylic salts, right? Here R chain is different, here R chain is different. In this case, you will have the formation of unsymmetrical ketones. Unsymmetrical ketones, right? Oh, Gina, don't worry. I have texted you in the in that Telegram channel. I have I have put the link. Okay, students, is this thing clear? Symmetrical, unsymmetrical. Is there any problem in this? Is there any problem in this, everybody? Is there any problem here? Right? Okay. Yes, very good. Now, next is from acyl chloride. Now, from acyl chloride, what you are going to do, right? From acyl chloride, so these are some of the very, very simple questions, right? So, from acyl chloride, a very, very important example, that is Rosenmund reduction, right? So, here we use Lindlar's catalyst, that is H2 catalytic hydrogenation in presence of BaSO4. Right, in BaSO4, that is acting as a poison, right? That is acting as a poison because we want to convert this acyl chloride just to CHO. We don't want to do further oxidation here, right? Okay, that's why what we are going to use further reduction. We don't want to do further reduction. That is why we just want to convert this Cl to hydrogen, so that we get this aldehydic group. That is why this is called Rosenmund reduction. This is called Rosenmund reduction. Okay. So, acyl chloride is hydrogenated over catalyst, radium or barium sulfate, that act as a poison, and this whole thing is called as Lindlar's catalyst. Right? Lindlar's catalyst, which is a poison, right? To stop the further reduction, right? So, here CuCl is converted to CHO. Then we have from acyl chloride one more method, and that method is with the help of alkyl cadmium, right? Dialkyl cadmium, right? So in dialkyl cadmium, what you will use, this alkane oil, this is your acyl chloride. What will happen, this R dash group here will replace this Cl here. This is by dialkyl cadmium, right? This is with dialkyl cadmium that this R dash will replace this Cl, and hence you will have the formation of this ketone, right? You will have the formation of this ketone, right? Next is from nitriles and esters. If we talk about from nitriles and esters, right? What is nitriles? Ester is C double bond O, O, R, right? What is nitrile? C triple bond N is nitrile. So let us see, same reaction we will use, that is Stephen's reduction. Nitriles are reduced to corresponding amines with stannous chloride in the presence of hydrochloric acid, right? Amines on hydrolysis give corresponding aldehyde. Let us see how. Now, you have RCN here with stannous chloride, that is tin chloride, this is SN, right? Stannous chloride and HCl, you will convert this is basically RC triple bond N, right? So, you are going to add hydrogen in both the cases, that will be H here and this is NH here. This is called imine. Further, this double bond on hydrolysis, this whole is converted to oxygen. That is why we will have the formation of aldehyde, right? That is how you have the formation of aldehyde from RCN, right? This is RC triple bond N. Firstly, you will break this fun bond and you will attach hydrogen here. Then further hydrolysis, this whole will be converted to oxygen. This is how aldehyde is formed from nitriles or cyanides, right? This is how aldehyde is formed from nitriles and cyanides. Yes, search and find from DNA batch. Very good. How's your preparation going? Yes. Okay. Hello. Nice to meet you as well. Right, ma'am, I'm from Andhra Pradesh. We want GOC. You want GOC? Perfect. GOC will be provided to you. Right, definitely that will be provided to you once we start the revision. Okay. Yes, everybody. Is this thing clear to you? Now, again, this pi bond will break and you will have the attachment of hydrogen in both cases. And then this NH will be eliminated and you will have the attachment of double bond O here. Right. This is called Stephen's reaction. Now, let us see with esters what will happen, right? So, first is your dibble. What is dibble? Diisobutyl aluminium hydride, right? Diisobutyl aluminium hydride. This is used for reduction, right? So, both esters and nitriles can be reduced to aldehyde by dibble. Right. So, directly we will see reduction must be carried out at low temperature. Hydrolysis of intermediates gives the aldehyde. Let us see the reaction. If you talk about the esters, right, you just need to have dibble, right, diisobutyl aluminium hydride. In that case, hexane at low temperature, minus 78 degrees Celsius, at such a low temperature, minus 78 degrees Celsius, right. Then after hydrolysis, you will convert this OH will be converted to hydrogen and hence you will have the formation of this aldehyde, right. Same is with this C triple bond N. This will be converted to CHO, right, with the same reagents, right. This is converted to CHO, right, with the same number of carbons, right, everybody. I think we are just left with 3-4 chapters, right? Once I complete those chapters, we'll start with the previous year questions and a lot of practice, right? Okay, because my lectures are going to increase on this channel so that we can complete your syllabus on time, right? And we can do a lot of practice, right? Now, students, tell me, is this thing clear? Now, next is acyl chloride, right? Next is this, so we have done, no? Acyl, this, so we have done. This, so we have done. Yes, this already we have done, right? Nitriles, treating a, yes. Now, from nitriles and Grignard's reagent, Grignard's reagent is going to behave the same way. It is going to behave the same way. Let me see CH3, CH2, C triple bond N, CH3, CH2, CH3, CH2, C triple bond N. You have the formation of attachment of this RMgX. Generally, I am writing the reaction here, right? We know that R is basically in terms of this is positive, so this will be negative. This definitely is negative, this definitely is positive. So this negative part will attack here, right? Then what will happen? You will have this CH3, CH2, C, this is N, this is double bond. One bond will break and this R will get attached here. And to this negative part, this positive part will be attached, that is MgX will be attached. Right? Always and always Grignard reagent will have the same process. Whether you talk about Grignard reagent with aldehyde ketones, whether you talk about Grignard reagent with carbon dioxide, whether it is with HCN or whether it is with CN, right? It will have the same thing, right? So here you will have the attachment of CR and this thing. Now after hydrolysis, this is CH2, this is Cr, this whole thing is converted to double bond O, and hence you will have the formation of ketones or aldehydes here, right? Okay, so here you will have the formation of ketone, right? This is how from treating nitrile with Grignard reagent, one more thing is formed here, right? Okay guys, understood? Everybody? Let us talk about aromatic compounds now. Yes, is this enough for? Definitely that is enough for advanced as well, right? I am teaching you both means and advanced, right? That is why I am taking up two parts here, right? Okay, otherwise so I could have completed this lecture in one go itself, right? Okay guys? Everybody in the chat box? Yes. Now everyone. If you see use of chromyl chloride here, right? Now let us see this thing here. Use of chromyl chloride, CR2, CrO2, Cl2. Now this chromyl chloride, basically it is red in color, reddish in color, right? And this reaction is very important, that is called Itard's reaction. The starting reactant is toluene here. This toluene to this CH3, it will react here, right? And hence after hydrolysis, this CH3 will be converted to CHO. That is called the conversion of toluene to benzaldehyde. And here in between you will have the formation of chromium complex, right? That means this two hydrogens, right? You will have CHHH. Three hydrogens you had. Two hydrogens will be replaced by OCrO HCl2. That is with this reagents that you have used here, right? Then you have the formation of this chromium complex, and after that this further will be reduced to benzaldehyde. Okay. Now next is oxidation of methyl benzene. Now this does not have a specific name. It is somewhat similar to Itard's reaction, but the reagent is different. The starting product is same, the end product is same, right? But what you have in the intermediate is different and the reagents are different, right? The reagents are CrO3, right? Plus you have an anhydride, acetic anhydride at room temperature, right? At a very low not room temperature, at a very low temperature, that is 0 to 10 degrees Celsius, right? 0 to 10 degrees Celsius, that should be the temperature. And chromium oxide along with acetic anhydride is used. You will have the formation of this complex which will further hydrolyze to give you benzaldehyde, right? Okay guys? Yes. Okay, definitely you can watch. Now, side chain. Now this is also very, very important. The reason why this is so important, if I say that the side chain, this whole CH3 will be converted to CHO, how? Now, we are doing the side chain chlorination. That means we are using Cl2 in presence of UV light. so that this follows free radical mechanism, right? And because of that, it's a very important thing that benzyl chloride is formed here, right? It's not like all this H will be replaced by Cl. Only 2 hydrogen is replaced by the Cl in the intermediate formation, right? And after the hydrolysis, you have the formation of CHO group, right? So in between what you have, that is benzyl chloride. That is called side chain chlorination by hydrolysis. Side chain chlorination tolerant give benzyl chloride, which on hydrolysis give benzaldehyde. This is a commercial method of manufacture of benzaldehyde, right? Then you have from hydrocarbons what is formed. First thing is Gattermann-Koch reaction, right? Gattermann-Koch reaction means to this benzene you will have the attachment of the CHO group, right? That means you are adding one more carbon into it, right? So basically Gattermann-Koch reaction was, you can say this was basically just like Friedel-Crafts acylation only. In Friedel-Crafts acylation we use CH3 C double bond OCl along with anhydrous AlCl3. Then you have the formation of this kind of electrophile which will attack on the, not like this, which will attack on the benzene, and hence you will have the formation of this kind of thing, that is C double bond O CH3, right? This is Friedel-Crafts acylation. What if I say I want to attach here this thing C double bond O H? That means I need this electrophile, right? That means if I follow Friedel-Crafts acylation, I will need this formyl chloride, right? I will require this formyl chloride. Then ma'am, why we are not using this formyl chloride? Why we are not using this? Reason being, this is very, very unstable, right? Because of the very unstable nature of formyl chloride, it is not used directly as Friedel-Crafts acylation. Rather, what we use CO with HCl, carbon monoxide with HCl, right? Then rest of the things are same, anhydrous AlCl3, CuCl, rest of the things are same only, right? And here, immediately, instantly you form this electrophile which will attack here, and hence you will have the formation of this aldehyde. Now this thing is called Gattermann-Koch reaction. How to remember this? This is KOCH, so you can remember CHO. Right, from benzene you have formed a CHO group here. That means you have attached the CHO group into the benzene. That is benzaldehyde is formed here. Right? Okay guys. Next is Gattermann formylation. Right? In Gattermann formylation, again you are attaching CHO group, but here in this case you have phenol. Right? Here you have phenol. To this phenol, it is not benzene, you have phenol. To this phenol, you are using ZnCN twice and HCl and then H2O. Then from here, you have the attachment of CHO group to the ortho and to the para position, right? Why the ortho is major? Because of hydrogen bonding here. Because of hydrogen bonding, ortho group formed will be the major product. This is in case of phenol. And the reagents are also different. The reagent is not CO, right? The reagent is not CO. The reagent is ZnCN twice with HCl. Here the reagent was COHCl. Here the reagent is ZnCN twice HCl. The reagent is different. That is why the name of the reaction is different. This is called Gattermann-Koch reaction. This is called Gattermann formylation reaction, right? Okay, everybody in the chat box, everybody, is that clear to everybody? Here it is phenol 2, we are using ortho and para position, we are attaching CHO group, but to this thing we are attaching it to benzene ring, right? Okay, that is the difference between Gattermann, Koch and formylation, okay? Okay guys, everybody in the chat box. Now this is Friedel-Crafts acylation reaction. You have RCOCl. Definitely you will have the formation of RCO positive electrophile, right? And then this is going to attack on this and you will have the attachment of CO, AR. AR means any aromatic ring or any alkyl ring, right? That will be attached here. right? This is Friedel-Crafts acylation, very simple reaction. Here you will have the formation of C2H5. This is C double bond O, this is positive. It will attack on ortho position or para position. In both the position it will attack, right, on ortho as well as on the para. This is ortho, this is para. On both the position it will attack. On ortho you will have the formation of CO-C2H5. On para also CO-C2H5 will be attached. Now this will be the major, this will be the minor product, right? Why this is the major product, can anybody tell me? Because here you don't have any hydrogen bonding. When you don't have any hydrogen bonding at the ortho position, that is why, because of symmetry, para is the major product, right? Okay, okay guys, okay, okay everybody. We have done the preparations of aldehydes and ketones. Now tell me, is there any problem in the preparation of aldehydes and ketones? Right? Is there any problem in the preparation of aldehydes and ketones? Everybody, is there any problem? Because after this, we are going to start with the chemical properties, right? We are going to start with the chemical properties, okay? Okay. Okay. Now, let us see the physical properties firstly. Physical property says that first thing is, yeah, these are physical properties, okay? Real life use of ketones, right? This is what I am telling you, right? So, only formaldehyde is a gas, right? Formaldehyde, that means HCHO, that is a gas. All other carbonyl compounds up to C11 are liquids and C12 onwards are solids, right? Only formaldehyde is a gas, right? And formaldehyde is used, like it is very, very smelly, right? And it is used in our daily life. You must have had like smell formaldehyde if you work in chemistry labs, right? So next thing is, low aldehyde give unpleasant smell. As I told you that formaldehyde has a very, very foul smelling. It is very foul smelling. So when you have the, you are predicting that which aldehyde is formed. So if you have a very foul smell gas, definitely that is formaldehyde, right? So higher aldehyde and ketones have pleasant smell, right? That is why higher aldehydes and ketones are used in perfumes, right? Because they have very good smell and they are liquids, right? Those up to liquids are used in perfumes, right? In fragrances they are used, right? Okay. Now, yeah, biolab too, it's not present in the biolab, but there must be some use of in the biolab also, right? Yes, mostly in chemistry labs, so I can definitely tell you. Bio, I am not sure about that, right? Because I am a non-medical student myself, right? So I've never been to a bio lab, but yes, in chemistry labs, definitely, right? Okay. Now, you have physical properties of K. So third thing is C1 to C3, formaldehyde, acetaldehyde, propionaldehyde. That means when you have 3 carbon aldehyde and acetone are freely soluble in water due to polarity of this bond. So basically they are saying that if you talk about the solubility factor, right, that is because of the hydrogen bonding with 1 carbon, 2 carbon, 3 carbon. Still it has less alkyl chain, that is why hydrogen bonding is stronger. But as you move ahead, as the molecular weight, that means the carbon chain increases, the solubility will decrease because the hydrogen bonding will decrease. Why the hydrogen bonding will decrease? For example, you have a very large R group here. So it will be very difficult for this oxygen to form hydrogen bonding with the water. That is why as the number of alkyl chain increases, that is why the solubility in water will decrease. And in case of ketone, only acetone will be soluble, rest of them will not be soluble. Reason being, rest of them will have large alkyl chains, right? Then C5 onwards are insoluble in water. After C5, they are completely insoluble because the molecular chain, molecular weight, the carbon has increased. That is why it will be very difficult to form hydrogen bonds with the water molecules. That is why it is insoluble in water. Right? Okay. The methone. Oh my god, yaar, you don't depress me like that. Methone does not exist. Ketone need to have at least 3 carbons. Ketone exists only from propane. Ketone exists. This is the lowest. This is the first member of ketone. First member of ketone which has 3 carbons. Methone, ethone does not exist. Okay, does not exist. Don't ask such questions, yeah. You are like preparing for JEE. Huh? Clear? That is why basics are so important. Please, please, please clear out your basics. Okay, please clear out your basics, because otherwise, it's not like JEE. Yeah, I understand that definitely in advance the questions are difficult, right? They ask you tricky question, and we are definitely going to practice those tricky questions. But for that, you need to have a basic. The base should be clear. If your base is not clear, then it will be difficult to solve the questions, right? So now you still have time, so don't be depressed, right? You still have time, focus on the basics, then practice a lot of questions, right? Okay. Then you have boiling point order. By boiling point order, now we are saying that alcohol, carbonyl compounds and alkanes. I used to teach offline, but now I am completely an online teacher, right? So alcohol, carbonyl and alkanes. We know that in alcohols you have hydrogen bonding, right? You have OH here, right? This is R. It is also OH. The hydrogen bond can also be with this oxygen, hydrogen bond with this hydrogen, right? So there are so many hydrogen bonds that can be formed here. That is why boiling point of alcohol is highest. Then you have carbonyl compounds. In carbonyl compounds, so basically it's like this. So this hydrogen will not show any hydrogen bonding. Hydrogen bonding will be shown by only this oxygen. Why this hydrogen will not show hydrogen bonding? Because this is not directly attached to any electronegative. So hydrogen bonding will be shown, but it will be because of this oxygen with the other hydrogen, right? Okay, so that is how the hydrogen bonding is not to that much extent here, right? Moreover, when you say that there have these kind of ketonic groups, right? So it will be even more difficult to show hydrogen bonding, right, as compared to alcohols. But when we talk about alkanes, there is no hydrogen bonding. No hydrogen bonding. Right? Okay. Next is destiny, I am saying. Okay. Destiny. Density of carbonyl compounds is lower than water, right? Carbonyl compound are less denser than water, right? With as compared to water, they have less density, they have less you can say bharipan, right? They are less dense as compared to water, right? Okay. Now we have also completed the physical properties. The next is the chemical properties of aldehydes and ketones, right? So everyone, do you want me to give you the break, right? Okay, now is it audible? Hello, hello, hello. Ma'am, you are on mute. I think now it's audible. By mistake, I turned it off. Now is it audible? Yes, everybody? Ma'am, speak loudly. I am speaking loudly only, guys. Right? Now, this is nucleophile. It will attack on this carbon, which is a polar carbon. Right? So now this is a polar carbon. This is negative. This is positive because of the electronegativity difference. That is why this nucleophile is going to attack on this carbon. Right? Nucleophilic attack from a direction perpendicular to the plane. Now, this is about the hybridization to the plane of sp2 hybridized orbitals of carbonyl carbon. Now, why this is sp2 hybridized? So, if you talk about this carbon here, carbonyl group is like this: 1 sigma, 2 sigma, 3 sigma. So, 3 sigma means definitely it is sp2 hybridized. That means it has an angle of 120 degree. So, can I say it has an angle of 120 degree, right? It has an angle of 120 degree, right? It has an angle of 120 degree. So, what will happen? They are saying that nucleophilic attack from a direction perpendicular to the plane of sp2 hybridized orbitals of, for example, this is my plane, right? This is perpendicular. The perpendicular plane is this one. So, it will attack like this, right? So, we are saying that this is our plane because this is sp2 hybridized means triangular planar geometry. Planar means in one plane it is, right? It is in one plane. Wait a minute, give me a second, right? I'm looking for a trigonal geometry kind of carbon. Yes, we have this here. So now this is the carbonyl carbon, right? So this is your carbon, this is double bond. I'm just assuming that this is double bond, right? And this is your one hydrogen or alkyl group. This is one hydrogen or alkyl group. This is, we are talking about carbonyl compounds. So because of the sp2 hybridization, that means they are sp2 hybridized, that means they are trigonal planar in nature. This is a plane, as you can see, this is a plane, these are all in one plane. So these are planar. Trigonal means they are in a triangular shape. So this is 120 degree angle. So now what they are saying that nucleophilic attack of the direction perpendicular to the plane. So this is the plane in which they are in. The plane perpendicular is this one. So to this direction it will attack, right? To this direction it will attack here. To this direction. So this is what we are saying. sp2 hybridized orbitals of the carbonyl carbon. Hybridization of carbon changes from sp2 to sp3. So now if I attach one more group into it, then definitely it will get converted from sp2 to sp3 and hence it will shift from tetrahedral. Why sp2 to sp3? Because now you will have, this is O negative, this is 111, this is nucleophile, this is some groups here. So now it will have 4 sigma bonds. 4 sigma bonds means it will be sp3 hybridized, right? Next is, they have shown you how it will be done. This is in one plane, nucleophile attack on the plane perpendicular to that, and hence after that you will have the formation of the tetrahedral shape, right? Tetrahedral shape will be formed, right? Okay guys, okay everybody, a tetrahedral shape will be formed because of sp3 hybridization, right everybody? Now next thing is, these are the reactions only, but before that let us see the reactivity here. Aldehydes are more reactive. Can anybody tell me why they are more reactive than ketones? Now, see one thing. You have, this is your aldehyde. This is aldehyde. Right? This is aldehyde. And this is ketone. And this is ketone. Right? And this is ketone. Now, if you talk about the aldehydes here, reactivity I want to check. Now tell me, if I talk about the nucleophilic addition reaction, what exactly is happening here? What it depends on. If it is more polar and this is more electron deficient, then nucleophile will attack easily, right? For example, this is your crush, right? Now this is you, right? You want to propose them. Now what should happen? Now this crush should be very depressed, very lonely, right? Then though you can easily, like you can easily be there, that shoulder, right? है ना? But if this crush, this C for crush, C for carbon, this crush is not very electron deficient, they are very happy in their life already, then they will be like, I don't need you, right? For you to attack this person should be more electron deficient. That is why this carbon, if it is very electron deficient, then nucleophile can attack easily. But if this is not electron deficient, it is like, okay, I am happy only in my life, right? Then this will not be able to attack, right? So now let us see what will happen. So in this case, let us see who is more, this one or this one. Nucleophile will find it easy to attack on this or this. Now here this alkyl group is donating the electrons. We know that it was partially positive, it was partially negative. It was partially positive, but this carbon has best friend called R. Only one best friend it has, right? This carbon has two best friends. That means this best friend and this best friend and this best friend. Two best friends it has. Now this best friend is going to do what and this best friend is going to do what, right? Okay. Now, for example, you are very depressed, right? You have only one best friend, right? And here you have two best friends. Now here two R groups are donating the electrons and making this carbon very happy. So this carbon is like, I don't need any external nucleophile here, right? But this carbon is like, I need external nucleophile. Why? Because to me only one R group is there. And if you talk about the methanol, methanol is even more depressed. Methanol is even more depressed. This is methanol, right? This is methanol. Methanol be like, I have no alkyl group. So I am very sad, right? So I am very sad. I am very electron deficient. I have no alkyl group. That is why this will have the maximum reactivity than this one, and this will have the minimum reactivity. First is your inductive effect. Because of the inductive electron donating effect of these alkyl groups, this carbon is not that much electron deficient so that it can attack one nucleophile. This here somewhat it is electron deficient, here so it is very electron deficient, right? First is inductive effect, second is steric hindrance. Now for example, this is that girl and here it has two best friends. So it will be very difficult for the nucleophile to attack because two bodyguards are already. Let us take these R groups as the brothers. Now if a girl has two brothers, now boys will find it very difficult to propose. Why? Because it has two R groups, big R groups, right? They will punch that nucleophile and say, get out of this the life of this girl. Now here it has only one bodyguard, only one brother. Here it has no brother, so nucleophile can easily attack here. So basically what I want to tell you that if you have steric hindrance, if already it has two alkyl groups, so the nucleophile wants to attack, but from where it should attack? It will be difficult for the nucleophile to attack. Here the steric hindrance is less. Here there is no steric hindrance, only two hydrogens are here. That is why it is very easy for the nucleophile to attack here, right? Okay. Great example, now no one will forget. I know that to teach Gen Z, you have to take out these examples only. Then only they will be like, yes, ma'am told about that girl. Ma'am told about that crush. No, yes, ma'am, I remember, ma'am. Then if I tell you that this is electron deficient, you'll be like, ma'am, what you are talking, ma'am? I am not able to understand, ma'am. If I talk like, okay, this is your crush and this is her best friends, right? So we know that it is very difficult, right? So when a girl has two best friends, right? So then nucleophile will find it very difficult to attack. Here it is still easy because only one competitor. Here there is no competitor, right? Okay. Okay guys, understood why this is so. First is inductive effect, second is steric hindrance, right? Steric factor, right? We need to find how to make ours our friend. What will be the catalyst? Very interesting thought, Abhishek. Abhishek is saying we need. Abhishek is clear. Abhishek is totally clear in his head. He's like, we need to make this our friend. Only then we can attack on the carbon. Smart. Smart. Okay, so now this was about inductive effect that I have taught you, and steric hindrance also, more steric hindrance in ketone, that is why it will be difficult to attack over there. That is why you will have this kind of reactivity order, right? One alkyl group, here you have two carbons and one alkyl group. Here you have two CH3s, right? Here you have CH2, CH3 on two sides. Here you have CH2, CH2, more inductive effect is there, right? Here you have more steric hindrance, that is why it is reactivity is very, very low, right? So based on the effects, this is the order that you will have, right? Okay, guys. Now after this, we'll start with the reactions, right? Different reactions with HCN, right? Everything will be same only, right? In this, we also do aldol condensation, Cannizzaro condensation, right? Tollens reagent, not Cannizzaro condensation, Cannizzaro, cross Cannizzaro. Then we will do reaction with the NH2 compounds, oxime, semicarbazide, semicarbazone, all of those things we will do. Okay? No, Drushyani, wait a minute. Dhanushri. No, Dhanushri, I don't take offline classes, right? I only take online classes. I teach in batches, right? Okay? Yes? Okay, everyone. So now I'm going to give you a break. Now, the class will resume. The class will resume in 10 minutes. What is the time now? It is 7:06. So the class will resume at 7:15 or 20. 7:15 or 20. How much break you want? How much break you want, guys? 15 or 20? Should I write 20 only? Let us write 20 only. 7:20 p.m. we will resume the class and we'll finish off the rest of the part. Okay? We'll finish off the rest of the part after the break. Is that okay with all of you? Is that okay? Chalo. Now, have your dinner, right? Take some rest, because the next part is going to be a tricky part, because we are going to do a very, very important reactions, right? Okay. 20? Okay, so the class will resume at 7:20. Hi everyone. So I am back. Everyone, am I visible? Am I audible to all of you? If yes, then write it down in the chat box. Let me verify if I am visible and audible to all of you. So now we are going to do nucleophilic addition reactions. Thank you so much. Thank you so much. Okay, so shall we start? Okay, so let us start. And the first reaction is addition of HCN, right? In the addition of HCN, right, what you will have? So first is this HCN is basically H positive and Cn negative, right? So if you talk about any reaction, let us take out ketones here. So this is C, this is basically R, C double bond O, and this is R, and here you are adding H positive, Cn negative, right? We know that the electrons are going to shift here, and this negative is going to attack here, so it will be RCO negative, and this is R, and here it will be Cn, right? And that positive will be attached here. Now this thing is called cyanohydrin. This thing is called cyanohydrin will be formed here, right? So reaction takes place in presence of mild base which attract H positive from HCN, right? It will take out H positive from HCN and produce Cn negative ion which acts as a nucleophile. Cn negative adds to carbonyl compound to yield corresponding cyanohydrin are useful synthetic intermediates, right? Okay, next reaction, this is the reaction that they have shown here. Next is due to steric hindrance, the rate of reaction in case of ketone is very slow. As I told you that ketones, because of steric hindrance, because of inductive effect, the rate of the reaction is very slow, right? So now we have NaHSO3H. So from here we can know that this is your positive part, this is the negative part here, right? So this will be the nucleophile, that is H, that is basically HSO3H, yes. HSO3, this is HSO3, right? It will attack from oxygen, so it will be OSO2H, right? From oxygen part, it will attack on the carbonyl. So your nucleophile will be O negative SO2H. That will be the nucleophile. Again, here electrons will jump here. This negative part will attack on the carbonyl carbon, the electrophilic part, right? So here the electrons will attack the negative, the nucleophile will attack here, and hence you will have the attachment of OSO2H, and this positive will attack on this because here it will become O negative. So Na positive will attack here and attach here, and hence your answer will be this one, and this is OSO3Na and OH, right? How? Because this H and Na will interchange itself, right? So proton transfer will happen, right? And hence you will have the formation of bisulfite addition compound that is crystalline in nature. This reaction is used for separation and purification of aldehydes. If you want to separate and purify aldehydes, because ketone will show really very slow reaction for this one, and aldehyde can show fast reaction and crystallizes out, so that you can separate out ketones and aldehydes here, right? Okay, so that you can separate out ketones and aldehyde in this question, right? Now this, so we have done the hydrogen sulfide addition compound and water soluble and can be converted back to original carbonyl compound with the addition of hydrolysis. If you do hydrolysis, that will be converted back to the original carbonyl compound. Next is its mechanism, as I told you here. Firstly, wait a minute, this is addition of Grignard reagent. If you're adding Grignard reagent, so with Grignard reagent also the same thing will happen. You will have, for example, you have R, this is R, this is R, this is R dash MgX, right? We know that this is the positive part, this is negative part, this is negative and this is positive. That means the electrons are going to jump here, the negative part is going to attack here, and hence you will have the formation of, this is C, this is R, this is R, this is O, MgX, and this is R dash, right? This is R dash, right? Very good. Now this is R dash, wait a minute. This is OMgX, right? Now after hydrolysis, this OMgX will be converted to OH. This is the reaction of ketones or aldehydes with the Grignard's reagent, right? Okay, so if you have a aldehyde here, then the answer will be, this is C double bond O, this is R, this is H, and with R dash MgX, what you will have, same thing will happen. This is negative, this is positive, positive, this is negative. R will attack here, and hence you will have R here. This is OMgX. This is hydrogen, and this will be R dash. And this MgX will be converted to H here. And hence, we can say that with the ketones, you will have the formation of 3-degree alcohol. With the aldehydes, you will have the formation of 2-degree alcohol. Now tell me 1-degree alcohol. If you want to prepare 1-degree alcohol, what you will do? If you want to prepare 1-degree alcohol, what you will do? If you want to prepare 1-degree alcohol, what you will do? Yes, everybody. Now, let us see this thing here. If you talk about methane, right? If you talk about methanol, this is hydrogen, this is C double bond O, this is hydrogen. Now, again, we are adding a Grignard reagent here, right? Again, what you will have, this is partially positive, this is partially negative, this is negative, this is positive, because electropositive atom is attached to the carbon. So here it will attack here, electrons will jump here, and hence you will have the formation of this C, H, this is OMgX, and here the attachment of R dash. Now, this after hydrolysis, this OMgX will be converted to H, and hence you will have the formation of 1-degree alcohol. So, these are the 3 things that you have, right? Okay, ma'am, why what RMgX? Ma'am, why RMgX is converted to OH, ma'am? Because of hydrolysis, because the second step is hydrolysis, right? After this, we also do acidic hydrolysis, right? After this, we also do acidic hydrolysis. Because of that acidic hydrolysis, this MgX part is replaced by this H, right? After acidic hydrolysis, right? Okay. Hello, Anusha. Okay, ma'am, electronic effect for class 11th. Okay, we'll do GOC. Don't worry about that. Right? So, 1-degree, 2-degree, 3-degree alcohol will be formed depending upon the reaction that you are doing here. Right? So, this is the mechanism. Right? In the reaction with methanol, you had the formation of 1-degree alcohol. If you react this with ethanol, not with methanol, other aldehydes, you will have the formation of 2-degree alcohols. If you talk about ketones, this is also aldehyde, no? Yes, this is also aldehyde. If you talk about, if you react this with ketone, then you will have the formation of 3-degree alcohols, right? Understood? Yes, everybody? 1-degree, 2-degree and 3-degree alcohols. Now, reaction with aldehyde. Now, if for example, addition of alcohols, aldehydes react with one equivalent of monohydric alcohol. Now, we are going to do this reaction with monohydric alcohol in the presence of dry hydrogen chloride, right? So, let us see. So, for example, here acetal, hemiacetal and ketal formation, and these are very, very important things. So, here you have aldehyde. This is with the primary alcohol we are reacting this in presence of HCl gas, right? All the things are important here. So, similarly, same thing will happen. Firstly, you will have R, C double bond O, and this is H. we know that this is positive, this is negative. So OH is going to attack here, right? So OH is going to attack here. Electrons are going to shift here. It will be O negative and here it will be positive, right? So here OH is going to attack on the negative position. So that means OH will attack here, right? This positive will be eliminated. Now this positive is going to attach here, that is this O negative will have the attachment of R dash, right? And what is this called? This is called hemiacetal, right? This is called, see, all the reactions, the mechanism is same. It is always what I am doing, I am making the negative part attack on the carbon and the positive part to this O negative. In all the reactions that we have done before, I am doing the same thing, nothing I am changing here, right? So with this thing is called hemiacetal. When to that carbon you have the attachment of one OR dash group, not OR group, and one is OH group. That is called hemiacetal. But when we talk about acetal, you should have both ROR groups, right? So what will happen? Again, you will add one more molecule of R-OH alcohol. Now what will happen? Now you will have the formation of acetal, right? So this OH will be replaced by this OR here, right? And hence you will have the formation of this acetal, right? So they can ask you, if you have dry HCl gas, this question has been asked, if you have dry HCl gas and you are using primary alcohols, then you will have the formation of hemiacetal. But if you use dry HCl gas in excess of the alcohol, then you will have the formation of the acetal, right? The formation will be acetal. What is hemiacetal? When to that carbon you have OR and OH. When to that carbon you have both the groups are OR, that is called acetal, right? So here hemiacetal further reacts with one more molecule of alcohol to give gem dialkoxy, known as acetal. Gem dialkoxy. Gem, I told you, gem means geminal. Geminal means on the same side. This you can remember with by, if someone is very loyal, we will say he is gem of a person, right? Gem of a person, geminal. With loyal will just one carbon. So these two OR dash groups, that is the same group, is attached to only one carbon, that is called geminal. Geminal dialkoxy, because this OR group is called dialkoxy, right? Next is the ketal formation. So for ketal formation, we will not use like simple monohydric alcohol. We will use dihydric alcohol, and that dihydric alcohol here we are using ethylene glycol, right? So ketone react with ethylene glycol in presence of dry hydrogen gas, right, to form cyclic product. So how it will form the cyclic product? This you can understand by write it in a different manner, right? So this is CH2OH, right? CH2OH, and this is also CH2OH, and this is ethylene glycol. So now what will happen here? What will happen here? This oxygen and these two hydrogens will be eliminated as water, right? Water will be eliminated and rest of the things will attach. This carbon will attach with this oxygen, this carbon will attach with this oxygen, and hence you will have the formation of this CRR as it is. This oxygen is attached to, this carbon is attached to this oxygen, right? This carbon is attached to this oxygen and rest of the thing is same, CH2, and this thing is called ketal, right? And here it is ethylene glycol ketal because it has been formed from ethylene glycol, right? Okay, understood? Yes, everybody? Everybody? Yes. Now, acetals and ketals are hydrolyzed with aqueous mineral acids, right? With aqueous mineral acids, they are getting hydrolyzed to yield corresponding aldehyde and ketones respectively, right? You will have corresponding aldehyde and ketones respectively, right? If they are further hydrolyzed with the mineral acids, like they will give back the aldehyde and ketones that they were formed from, right? Next thing is addition of ammonia, right, and its derivatives. So now let us see that how ammonia, and this is very important because here not only we are going to talk about just ammonia, but also its derivatives, from which you will see 2,4-DNP, you will see semi-carbazone, you will see Schiff's base, oxime, so many things you will see, right? Okay, hydrazine, hydrazone, all these reactions are very, very, very important for you, right? So let us go through that. Okay, guys, so let us go through that. Wait a minute. Yes. So basically right now, so just they are telling you that what is happening here, right? So you have carbonyl and you have NH3, right? Now this lone pair, it has base. Now what is the work of a base, right? A base is a proton acceptor, right? So firstly, this ammonia is a base and it is also electron rich because of the lone pair here, right? So ammonia, can it act as a nucleophile because it is electron rich? It is electron rich means it is acting as it has more electrons, it is negative nucleophile, right? So it is acting as a nucleophile here, right? Now not as a base, right? Yes, ammonia is a base, but ammonia is not abstracting any proton here, right? It is not accepting any proton here, rather it is acting as a nucleophile here, right? So in this reaction, that ammonia is acting as a nucleophile. The nucleophile will attack on the positive charge, right? The carbonyl carbon of the carbonyl carbon, which is positive electron deficient. Electrons will jump here. This is negative, and it will be NH2 and H. Now there will be internal transfer of the hydrogens, right? This electron, these electrons are going to jump here. Now firstly tell me why this NH2 has positive charge. Because here nitrogen is attached to how many bonds? 1, 2, 3, 4, right? 4 bonds it is attached to, right? 2, 3 hydrogens and 1 carbon. That is why when nitrogen has 4 bonds, it has positive charge, right? Okay. For example, oxygen usually make 2 bonds. When it has more than 2 bonds, it will be positive charge. Nitrogen usually make 3 bonds. When it has more than 3 bonds, it will have be positively charged. So now to eliminate that positive charge, as the electron negative element cannot handle a negative charge, that is why it will take out the electrons from here and it will be donated to the nitrogen, and hence this hydrogen will be internally shifted to this O negative, and hence you will have the formation of OH here and NHH here, right? Even now the reaction is not completed yet. Again, we know that this has lone pairs because it has 3 bonds, it has lone pairs. Again, these lone pairs are going to shift on this carbon, right? And hence you will have the formation, and this H will be eliminated, right? And hence you will have the formation of this imine, right? Okay, hence you will have the formation of this imine. So easy way to remember this is very simple, right? You have C double bond O. I'm telling you the easy way to remember this. C double bond O, and here you have NH2H, or you can say NHH2. Water will be eliminated, rest of the things will be same, right? And the answer will be C double bond NH. This thing will be the answer, right? This thing will be the answer. Now if I give you a general view here, if you replace this nitrogen, this hydrogen with Z, then always you will have NZ here. This will be always the final product, right? You will always have NH2 and something Z here, and the answer with any ketone or aldehyde will always be double bond NZ, right? Okay guys, understood this? This is the main important thing about this reaction. Okay, everybody in the chat box? Yes, everybody in the chat box. Now let us see what kind of different reactions that you can see here. First is, as I told you, that water will be eliminated from this side, and hence you will have the formation of C double bond NZ. Now what are these different Zs? Let us see. If your Z is hydrogen, so now firstly let us see what will be formed. This is C double bond NZ, right? So if this is hydrogen, you will have the formation of H here. This is nothing but this is called imine. This is called imine. For example, you have this group as R. For example, that was R, right? For example, you had RNH2. What is RNH2? That is amine only, right? So hence you will have the formation of C double bond NR, and that is called Schiff's base, right? That is called Schiff's base. If you talk about hydroxylamine, that means if you replace this R with OH, that means if you have NH2OH, right? In NH2OH, here this R will also be replaced by OH, and hence you will have the formation of oxime, that is C double bond NOH. Now, if you have hydrazine, what is hydrazine? For example, this OH is replaced by NH2. That means Z is NH2. So this OH will also be replaced by NH2. Now, what is this called? This is called hydrazone. Okay, this is called hydrazone. Okay, guys, this is called hydrazone. Yes. So now this is called hydrazone. Understood, everybody? Understood, everybody? Now, I'll send you one. I want all of you to do some reaction yourself. That is your homework, right? So I'll send you one page of your NCERT, right? Where semicarbazone 2,4-DNP, right? Then you have semicarbazone, carbazone, hydrazone. I think two, three reactions you have, right? Where this hydrogen is replaced by a phenyl group, right? Then there is replacement of, on the second and fourth position, you have the attachment of NO2 group, right? That is why 2 and 4th position you have nitro group, right? So this is your homework to go through that table, right? I'll send that table on my Telegram channel, that is Diksha Kaushal Chemistry Official, right? Okay, so I'll send that table on our Telegram channel, right? Okay, now next is reduction. Now this was about the how to react ketones and aldehydes with some NH2 or the derivative of NH2, right? Ammonia or the derivative of ammonia. Next thing is reducing agent. By reduction, what you can do? So basically you have 4 reducing agents. One is H2, then NaBH4, LiAlH4, and aldehyde give primary and ketones give secondary. Now let us see. These are the reducing agents that you have. Reduction to alcohols. Now have we done this? We have already done this in alcohol, phenols and ethers. Alcohol, phenols and ethers we have already done. That we have done not in the properties, we have done in the preparation step of the alcohols. How by reduction from aldehyde and ketones you can form alcohols, right? So here you have this thing. First is catalytic hydrogenation. That is not at all selective in nature, right? It will also do reduction of double bonds as well, right? So this is not at all selective. NaBH4 and LiH4, right? These are specific reagents, right? So let us see that. So if you talk about the reducing agent just by the hydrogenation, right? So here, if you have aldehyde, that is converted to 1 degree. If you have ketone, that is converted to 2 degree alcohols, right? If you have aldehyde, that is converted to 1 degree. If you have ketone, that is converted to 2 degree alcohols, right? Now, let us see. Here 3 things we have already done, right? We have already done the reduction for esters, right? We have done the reduction for carboxylic acids, right? So all of these things we have already done in alcohol, phenols and ethers, right? I have completed that thing there, right? So you can see that in detail in that lecture, right? So now next is you have reduction to hydrocarbon. So you have 2 things here. If you want to convert if you want to convert aldehydes not to just alcohols, you want to convert it directly to hydrocarbons, you have 2 reactions. One is Clemmensen reduction, other is Wolff-Kishner reduction. If you talk about Clemmensen reduction, in this you have C double bond O, zinc amalgam with HCl. It is in the acidic conditions, right? In the acidic condition, this ketonic or the aldehydic carbonyl group will be replaced by 2 hydrogens here, right? But if you talk about the Wolff-Kishner reduction, in that case, you have basic condition, that is KOH and ethylene glycol. It is having the basic condition, and in these basic condition, you will have the formation of this double bond O will be converted to 2 hydrogens here, right? Remember one thing, for example, here in the acidic condition, you have a compound which is having double bond O and it is also having COOH. Now, the answer will be this, only this thing will be replaced. There will be 2 hydrogens here. But in the acidic condition, because this is the acidic condition, this is the acid. So, there will be no reaction on this COH group, because in acidic condition, acid will stay as it is. But if you have the same compound here, if you talk about the same compound here in this case, you have double bond O here and this is COH. Here things will change. Here what will happen? Definitely the double bond O will be converted to 2 hydrogens, but this COH group will also show the neutralization reaction in the basic medium, right? Okay, it will also show, so it will be COOK. It will form a salt here, right? It will form a salt here. Right, students, everybody in the chat box, is that clear or not? Is that clear or not? It varies with the acidic and basic condition. Double bond O will always be converted to hydrogens, but with other things like you have acidic group, in this case, nothing will happen to the acidic group. But in this case, it will form a salt, that is COOK, right? Okay. Okay, students. Now, next thing is oxidation. Now, oxidation, mainly we have 3 reagents, that is Tollens reagent, right? Then you have Fellings, then you have Benedict, right? Now, let us see Tollens, Benedict and Felling. Aldehydes are easily oxidized to carboxylic acids on treatment with common oxidizing agents like HNO3, KMNO4, K2Cr2O7. It can be easily oxidized to carboxylic acid. Now we are talking about some specific things. Now see, if you talk about HNO3, KMNO4 and K2Cr2O7, they are strong oxidizing agents, right? They have no biasness with whether it's aldehyde or ketone. But when you talk about Tollens and Felling solution, some will show Felling, some will show Tollens. Now we need to see that which will show Felling, which will show Tollens, right? If you talk about ketones are generally oxidized under vigorous condition. Tollens and Felling both will not show oxidation of ketones, right? So at elevated temperature, the ketone oxidation involves carbon-carbon bond cleavage and form mixture of carboxylic acid having lesser number of this. Now they are saying that if you talk about the ketone, now here we are just talking about the ketone, not about the carboxylic, not about the aldehydes, right? So ketone need vigorous condition to give oxidation product, right? So what will happen to ketone? A bond will break here. Here you will have the attachment of OH. Here this will be double bond O and here it will be OH. So basically carboxylic acids will be formed. What you need to do? Break the bond, right? Break this bond and hence with the same number of carbon form the carboxylic acid. Second question that arises, ma'am, why you have break this bond? Why not this one? Why you have not break this bond and you have the formation of methanoic acid and propanoic acid? What is the reason? Reason is Popoff's rule, right? In Popoff's rule, what is said? The CO of unsymmetrical ketone will always stay at the side where smaller alkyl group is present, right? So when you want to break it, firstly you need to see which has smaller alkyl group, this one or this one. Definitely this alkyl group is CH3, here it is C2H5. So CO will stay with the smaller alkyl group and hence this bond will break and hence you will have the formation of 2 carboxylic acids, right? Yes, definitely Jones reagent is an oxidizing agent, right? Definitely it is an oxidizing agent, right? But that is not used to oxidize aldehyde and ketones, right? Now, if you talk about this thing here, tell me, you have CH3, CH2, CH2, C double bond O, CH2, CH3. I'm asking you whether this bond will break or this bond will break. This is A, this is B. According to the Popov rule, tell me which bond will break, A or B. Which bond will break, A or B? A or B, which bond will break? Everybody in the chat box, see? This thing is C2H5 and this alkyl group is C3H7, right? These are the two alkyl groups that you have, isn't it? These are the two alkyl groups that you have. Now, these are the two alkyl groups that you have. Which is smaller? This one is smaller. So, CO will stay with this one, hence this bond will not break, this will break, and hence you will have the formation of CH3, CH2, C. This bond will break, right? This bond will break. Wait a minute. This bond will break. That is why you will have the formation of the same number of carboxylic acid, same number of carbon, CH3, CH2, COH. Again, CH3, CH2, COOH. This is how to utilize Popov rule and make, from ketone you have to make carboxylic acids, right? Okay? Okay? Yes. Now, let us see what about oxidation of Tollens test. If you talk about Tollens test, if you talk about Felling's test, what will happen? If you talk about Tollens test here, Tollens reagent, that is ammonical silver nitrate solution, right? In this is ammonical, this Ag positive will be converted to Ag, and hence this is Ag silver mirror. Hence on that tube you will have the formation of silver mirror, right? The Tollens reagent ammonical silver nitrate solution, the test is given by, very important, aldehydes only, and that too specifically aliphatic aldehydes, right? Both, wait a minute, this test is used to just, okay, yeah, this test is given by both aliphatic and aromatic aldehydes, and this is, ketone will not give, because ketone have very vigorous conditions, right? It needs very strong oxidizing agent, and Tollens reagent is a mild oxidizing agent, right? So that is why aromatic and aliphatic aldehydes will give this reaction, right? And what is this reaction? Here what will happen? You will have aldehydes, right? That will react with ammonical solution, ammonical nitrate solution. This is basically Ag positive here, Ag positive ions. That will be converted to Ag, and hence if you see this reaction here, positive to 0, that means oxidation number is decreasing. That means here you have reduction, and here definitely you have oxidation, because aldehyde is getting converted to carboxylic acid here, right? Okay. Yes, everybody. What you can't understand? Dhanushri, is that clear? Yes, everybody, is that clear? Now, second is you have Felling test. Now, if you talk about Felling test, it has two kind of solution. One is Felling A, other is Felling B. Felling A solution is copper sulfate solution, right? And Felling 2 solution is alkaline solution of sodium potassium tartrate, right? Benedict is also same as Felling only, right? This is also called Rochelle salt, right? Felling A and B mixed in equal amount before the test, and the difference between Felling and Benedict is that Felling solution, it has to be prepared immediately, right? You can't store it. That is why Benedict is preferred. In Benedict solution, all the things are same. The difference is here you use citrate, right? That is why you can prepare this before and it will stay. It can be stored, right, for some time. That is why we prefer Benedict solution over Felling test, right? Rest the test is same only, right? So this is the Felling test. In Felling test, what you will see, this is basically your sodium tartrate solution, right? Felling B. This is Felling B. This is Felling A, which reacts with the base to form CuOH twice, right? This is your Felling A, right? Now when these two will react, they will give you a deep blue complex. This is when you will mix the equal amount of phelling A and phelling B. You will have deep blue complex, right? Now you have mixed phelling A, phelling B. Immediately you have to do that, right? Now after this, you will react aldehyde with Cu2 positive ions. This will be converted to, instead of deep blue color, you will see brown red, brick red color. Brick red precipitates you will see. Right? Those brick red precipitates is of cuprous oxide, and that means here Cu2 positive, it is converted, it is getting reduced here, and here it is getting oxidized here, right? In tolerance test you will see silver mirror, but in Fehling test you will see red precipitates, right? Brick red precipitates you will see, right? Okay, okay guys, okay everybody. Wait a minute, just give me a second. Both aromatic aldehyde. Just give me a second. Just give me a second. Just give me a second. So write one thing here, right? Write one thing here, mention one more point here that is important, right? That is, it is given by only aliphatic aldehydes, not by aromatic, right? So if you want to separate aldehydes and ketones, then you can use tolerance test, because positive test will be given by tolerance and negative will be given, positive test will be given by aldehyde, negative will be given by ketones. But if you want to separate, if you want to distinguish between one aliphatic and one aromatic aldehyde, then you have to use Fehling test. And or Benedict also you can use, right? That is the same thing, only the difference is just it is stored and Benedict is not, Fehling is not stored, and Benedict you have to store. You can store that thing, right? So that is beneficial for you, right? So next is oxidation of methyl ketone. So now this is basically Hydroform test. Now important thing about Hydroform test is that if you talk about ketones, it need to have this thing. Ketones or aldehydes, only those ketones or only those aldehydes which have CH3 C double bond O group can show positive haloform or Hydroform test, or it should have CH3, you just need to add hydrogens here, so it will be this thing, or this kind of alcohol will show positive Hydroform or Haloform test, right? Okay, so these are the two conditions. So it is not specified to whether it's aldehyde or ketone or alcohol, this kind of aldehyde ketones and this kind of alcohol, right? Now next thing is aldehydes and ketones having at least one methyl groups linked to carbon and carbon give this test. Methyl ketones react rapidly with, now what will happen, methyl ketones which have one CH3, they will react with Cl2, Br2 or I2 in the presence of alkali to give haloform or acid salt. Now what is this haloform? Haloform is basically CHX3, right? Famous thing is CHI3 which is of yellow color, and this question is also asked frequently regarding haloform, right? So now here you have the test, haloform test. What exactly you have? The reagents are NaOH, or they can also give you NaOH with X2, Both are the same things because after this they will form NaOH only, right? Because it has this group, that is why it will show positive iodoform test or haloform test, and here this will be converted to ONA, right? And the rest, this CH3 will be converted to CHX3. This CH3 is converted to ONA, right? And this will be eliminated from this compound and it will be converted to CHX3. That is called the haloform, right? That is called haloform, right? Okay, guys. Okay. Now, oxidation of methyl ketone. Again, we have some examples, right? This is converted, right, to CHBr3. Now, here you have, see, very important thing about haloform test is double bond will stay intact. Double bond will stay intact. There will be no change in the double bond, that will stay as it is. This CH3 will be converted to ONA and hence you will have the formation of CHX3. And here X is Cl, so CHCl3, right? So this is converted to ONA and you have the formation of CHCl3. How you knew that this will give the positive test? Because you have COCH3, right? This is the main condition for haloform test, right? Okay. This oxidation does not affect carbon-carbon double bond if present in the molecule. This reaction is used for detection of CH3CO group, or very important, or you have this group that I showed you, CH3CHOH group that I have already showed you, group which produces CH3CO group on the oxidation. It will further oxidize and produce the same thing that was required, right? Okay, understood? Understood, everybody? Oxidation, tell me, in ketones. Oxidation in ketones, where we did oxidation in ketones? Oxidation in ketones, okay, this one. Oxidation in ketones simply means that you need to, it will firstly happen by any oxidation. You need a very vigorous conditions for oxidation of ketones, right? Very vigorous oxidizing agents like HNO3, right? Very strong oxidizing agents. Now what you need to do? You need to break the bond. You have this carbonyl, break either this bond or this bond, and with the same number of carbons form carboxylic acids. Now the question is, should this bond will break? Should we break this bond? The answer lies here. The answer will lie here. Should we break this bond or should we break this bond? Right? What is the correct answer for that? Should we break this bond? Should we break this bond? The carbonyl carbon will stay with one which has less which has less carbon in the alkyl group. So here, why we have break this bond? Because CH3 has less number of carbon instead of C2H5. That is why this carbonyl will stay with this CH3, right? Okay. Similarly here, this has less number of carbon. That is why carbonyl will stay here and this bond will break. Okay. Okay, everybody. Okay, ready? Understood? Understood now? Understood now? Now, next reaction is halogenation reaction, right? So similarly, we are doing that mechanism involved. So let us see what is the mechanism. So first step is halogenation. That means this H3 will be substituted by Br and hence you will have CBr3 here. Then you will have the addition of the base, right? What the base will do? This ONA will substitute this CBr3 here and hence you will have the formation of this is H, CHBr3 and this ONA will be substituted here and this will be ONA here, right? So that is the mechanism of haloform, right? Now let us see what is Aldol. Do you want me to do Aldol today itself or in the next class? Yes, everybody, do you want me to do Aldol today or in the next class? Let us do this today only, है ना? Let us complete aldehydes and ketones today itself, okay? Shall we complete aldehyde and ketones today itself, right? Okay? Carboxylic acid we will do in the next class, okay? Now, let us see this. If you talk about the aldol condensation, I will give you a very direct, simple method, right? Basically here, what we are going to use that aldehyde or ketone which has alpha hydrogen, right? There should be alpha hydrogen first condition. Dilute base is used here. Right, so aldehyde and ketones with at least one alpha hydrogens undergoes a reaction in the presence of dilute alkali as catalyst, right? Then you have this thing on heating the aldol and ketone, right? If you have aldol or ketone, readily lose water to give alpha beta. Now you'll be like, ma'am, what is this, ma'am? Let me take an example for you. Okay, this is written here. We'll show that how this is formed. You have CH3, CHO. The trick to answer this is, right, how to answer these kind of questions, right? Okay, definitely Sindhuja, you can definitely watch this, right? So this is CH3, CHO. What you need to do, this is CH3. Firstly, write and open the carbonyl group. Then open the alpha hydrogen. Right? This is alpha hydrogen, right? The carbon next to this carbonyl is alpha and the hydrogen attached to that is called alpha. Now what you need to do, you need to form the products here. So very simple, right? Very simple. You need to attach these two things. That means what you need to attach here, the carbonyl carbon with the alpha carbon. Everywhere we will do this thing. So this is CH3, this is C, double bond O, this is hydrogen. This will be attached to this carbonyl carbon. Here you have this hydrogen. Here you have this CHO. Ma'am, what is this? Now, we will attach this but in a very different manner. This I just showed you how to attach it, right? So why I have opened that carbonyl carbon? Because you need to convert this carbonyl carbon to OH. Then you will attach it here, right? Here you will have one hydrogen, right? Rest of the things will be same. This alpha hydrogen is shifted to this position. This alpha hydrogen is shifted to this O negative here. Basically what is happening? We know that this is positive, this is negative. Electrons are shifting here. That is why this H positive, this will be H positive and here it will be OH negative. Basically this is H positive. What will happen? No, this will become CH2 negative and CHO and this is H positive. That is why H positive will attack there and CH2 CHO will attack on the carbonyl carbon, right? Okay, that is why I have told you the direct simple trick here, that attach the carbonyl carbon with the alpha carbon. Here CHO will remain as it is, but here double bond O is converted to OH, right? Now then they are saying it will lose water, right? Lose water from alpha and beta position. This is CHO, this is alpha and this is beta. Alpha will lose OH and here you will have H, here you will have H, right? This is the hydrogen, right? Here you will have H, this H positive will be eliminated, this bond is shifted here and hence you will have the formation of, this is CH3, this is C, double bond, this is CH, CHO, right? Okay. This is called alpha beta unsaturated because you have unsaturation or alpha beta unsaturated aldehyde, right? Because this is alpha and this is beta. If you talk about this, here it is aldehyde and aldehyde and alcohol. That is why it is called aldol, right? And all these steps are called aldol condensation because here you have taken out water, right? Okay. Benzaldehyde shows Cannizzaro reaction. That does not show aldol condensation, right? Okay. So that was the first example. In the second example, they have taken up CH3COCH3. So let us take that. So same way we will do. CH3C double bond O. This is CH3. Firstly, so I will in one in one molecule, I will open the carbonyl compound, carbonyl group. In the other compound, I will open the alpha carbon. This is COCH3, right? This is my alpha, this is my carbonyl. So these two will attach to each other. So it will form CH3, C, this is O negative, this is CH3. This CH3, I have just written the CH3 here. This will attach to CH2, CH2, CO, then you have CH3. This hydrogen, alpha hydrogen will be shifted to this oxygen. So here it will be OH. And that will be the answer. And that will be the answer. And that will be the answer. This will not be aldol. It is called aldol, but actually it is ketol. Because you have ketone and you have alcohol. It is actually ketol. Right? Now, again what will happen? This is alpha and this is beta. From alpha and beta position, you will eliminate the water here. Right? Water will be eliminated. Right? Water will be eliminated. Let us see. Water will be H positive eliminated here. Double bond will shift here. OH negative will eliminate from this side. This is CH3, C, double bond, CH. This will stay CH3, CO, CH3. So that will be formed here. Right? Acetaldehyde and acetone. Why this is confusing? See, one very simple thing. Okay, I'll do that. One very simple thing that you need to see here. This is your ketone, right? You just need to attach the carbonyl carbon of one molecule and the alpha carbon of other molecule, right? And when you are attaching the carbonyl carbon of one molecule, here double bond O is converted to OH. And here carbon is connected here, that we can see only. This is converted to OH because of this hydrogen is shifted here. Right? Okay. Tell me, students, is there any problem in this particular case? In this particular case, carbonyl carbon is attached to the alpha carbon of other molecule, right? Where you have attached the carbonyl carbon, that carbonyl carbon is converted to OH. Rest of the things remain same, right? Rest of the things will remain same, right? Okay. Okay. Now things will be confusing because now we are going to use two products here, right? Now I am going to use cross aldol condensation. Right, cross aldol condensation. Firstly, let me show you the mechanism here. Mechanism is not that important for you, right? But still, let us see. We know that mechanism is very, it is very long mechanism. But still, if you want to understand, let us see the mechanism here, right? So base will try to abstract the proton, right? So base will abstract the proton firstly. And it will abstract the proton from alpha because alpha hydrogens are very acidic in nature, right? So it will abstract the proton from the alpha position. This is the alpha position. Proton will be abstracted and negative charge will be on the carbon, and hence you will have the formation of this thing. Now this is the nucleophile that is formed. This is a nucleophile, right? Next thing is you have another molecule. Here we know that what will happen, this is partially positive, this is partially negative. Because this is positive, that is why this nucleophile is going to attack on the carbonyl carbon and the electrons will jump here, and hence you will have the formation of O negative here. And to this, H positive will be attached here, H positive will attach and hence you will have the formation of the same thing that I have formed, that is aldol product. After that, on heating, OH negative will be eliminated, H positive will be eliminated, hence you will have the formation of alpha beta unsaturated aldehyde and ketones. Yes, everybody, is that clear or not? Is that clear? Is that clear? Is that clear, everybody, or not? Yes, everybody, is that clear or not? Good? Yes, very good. Now, next is cross aldol condensation. Now, cross aldol means you have two different products, different reactants. Rest of the things are same only. Now, they are giving you ethanol and propanol. Right? They have given you ethanol and propanol. Now let us see with ethanol and propanol what will happen. Right? So with ethanol and propanol, 4 products will be formed. CH3, C double bond OH, ethanol. Propanol is CH3, C double bond. Let's take ethanol and propanol only. CH3, CH2, CH2, C double bond OH. Right? Now I have these 2 products, reactants. So 4 products will be formed. One is, what if this ethanol is reacting with another molecule of ethanol only? Right? So it will be self-aldol. It is reacting with its own molecule. That is why I'll do same answer I will form, not answer, same method I will use. If it is reacting with its own molecule, self-aldol will be done, right? So what will happen? This ketonic, this carbonyl will be attached to the alpha carbon, right? And hence you will have the formation of, this is CH3, C, this is OH, this will be converted to OH, this is H here, this is CH2, and this is CH2. That will be formed, right? After that, after eliminating water, OH negative from this side, H from this side, you will have CH3, CH double bond, CH, that will be formed. That is the first product that will be formed, right? Okay, that is the first product that will be formed. Is that clear? That is the first product that will be formed. Second is, what if ethanol is reacting with ethanol? So what if ethanol is reacting with, not propanol is reacting with its own molecule? Then you will have one molecule where CO group is opened, one molecule where alpha group you will open. What is alpha? This is alpha, no? So alpha carbon you have to open. This is CHO. This is alpha. Here you have to open the alpha hydrogen. Then this will be CH2 and this is CH2. Biggest mistake that students do. They think that they will eliminate hydrogen from here. What they do, they attach this carbonyl carbon with this carbon. No, alpha, alpha, I'm again saying alpha, 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 alpha. Alpha means this is alpha, right? So here, this carbon will be attached to this carbon. That is alpha carbon. Rest of the things will remain same. So what you will have, CH3, then you have CH2, then you have CH2. Then this carbonyl carbon is converted to OH. Rest of the thing is same. Just attach this carbon to this CH. To this CH you have the attachment. This will be eliminated. This will be eliminated. To this CH you have the attachment of CHO group. Then you have the attachment of CH2, CH3. Basically this is CH3 only, no? So this is CH3. Okay. This will be formed. Now after this, we know that what is alpha? This is alpha and this is beta. Alpha, you will eliminate H from there. Beta, you will eliminate OH from there. You will have the formation of CH3, CH2, CH2, C double bond, CHO, CH2, CH3. This will be formed here, right? Okay, understood? Yes, everybody. Now, one more thing can happen. What is that thing? That carbonyl carbon of ethanol and alpha carbon of propanol. Alpha carbon of propanol means something like this. They too can react. So carbonyl carbon will react with the alpha carbon. What will be formed? This is CH3. This is carbon. Here carbonyl carbon you have, that is why it is converted to OH. Here it is H. Now this carbon is linked to the carbon here. So here this is carbon. It is H is eliminated from here. It has one hydrogen. It has this CHO group. Then it has CH2, CH3. this thing will be formed here. Students, tell me, are you clear on this part? Why in cross aldol you have different products, right? Okay. You have mixture of products here. After this is alpha, this is beta. Again, H will be eliminated, OH will be eliminated. You'll have the formation of CH3, CH double bond, C, HO, and this is CH2, CH3. Right? Okay. One more thing can happen. What if ethanol is like, I want to use my alpha hydrogen, and propanol is like, I want to use my carbonyl carbon. So what we'll use? The one which is using alpha hydrogen, we will not talk about only. We will not talk about the carbonyl carbon of that thing, right? We will not talk about that, right? So here, wait a minute, this is CH3, CHO. This CH2 alpha will be opened, right? This is alpha. That is why this carbonyl carbon is connected to the alpha carbon, and hence you will have the formation of CH3, CH2, CH2. This carbon is converted to OH, right? Hydrogen will stay here as it is, but this hydrogen will be eliminated because it will jump to this side, and this CH2 will be attached here, right? After that, you will eliminate water from here, right? Then you will have CH3, CH2, OH eliminated from this side, this from this side, the CH2, 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 C double bond, CH, CHO. This will be formed in the end, right? Okay, kids. Now tell me, is there any problem in cross aldol condensation, how to form different products? One of the students was saying that, ma'am, please do it for CH3, CHO and CH3, C double bond O, CH3. Now, this is your homework. The same way you are going to do this. Firstly, react aldehyde. The product will be same only as that we have done, right? Ethanol with ethanol, that is acetaldehyde with acetaldehyde, that ketone with ketone. But this again has alpha hydrogen also. Again, ketone with ketone, right? Then aldehyde with ketone, aldehyde with ketone, right? Okay. So that is your homework. Let me see if you're able to answer this or not. Try it. We will do that in the next class. Try it. It's a very same thing you are going to do here. Same thing that we did here. Same ditto, copy, paste, same thing you are going to do. Right? Try to do this yourself. If you're not able to do that, I'll do that in the next lecture. Okay? Understood, guys? Oops. Yes. Now, I'm writing it here. That is your homework. Right? Okay? Yes, I will do it to give 4 products. Very good. Ready? I'll wait for that in the comment section. Right? I'll wait for that in the comment section. If you're able to do this, just write yes, ma'am. And best will be if you can give me the IUPAC naming of the products. That will be best thing that you can do. Right? Okay. Now, next is cross aldol condensation. We have already done that. Right? Here, cross aldol condensation will have very less products. Can you tell me why? Can you tell me why the mixture of product is not formed? Because it does not have any alpha hydrogen. No alpha hydrogen. Only this has alpha hydrogen. Only this has alpha hydrogen. So what will happen in this case? The one which does not have any alpha hydrogen, it will have carbonyl compound, right? The one which has alpha hydrogen, it will be C double bond O, CH2, CH2H, CH2NH. Now, what will happen here? Just eliminate this CO. Just don't open this, otherwise so you will get confused only. Right? Now you know that this is alpha and this is, wait a minute. Now you know this is alpha and this is your carbonyl. They two should attach to each other. Right? They two should get attached to each other. This is alpha and this is the carbonyl carbon. So what we will do now, we'll attach these two things here, and it will be 1, 2, 3. This is C. This will be converted to OH. Same thing I am doing. Because this is carbonyl, this is converted to OH. H will stay as it is here. This is connected to this alpha carbon, right? And here hydrogen will be eliminated, right? That is why I am not writing any hydrogen here. Rest of the thing is same, right? Isn't this the right answer? Right? Here the mixture of product is not formed. Reason? Because here we have only one have alpha hydrogen. That is why mixture, 4 products are not formed here. Right? Okay? Ma'am, teach amides. Yes, after completing aldehyde ketones, I am going to teach you amines only. Amines, amides, all of these things we will see. Next is intramolecular aldol condensation. Now they are saying intramolecular, and within a molecule, how can it happen? So you have 2 CO groups. It is having carbonyl, okay? This is having alpha. So I am going to do the same thing here, right? One, two, and this is the third one, right? So now students see one thing. Both of them have alpha, right? So now let us see one thing. I'll not write here C double bond, or rather I'll just write CO, and this is CH2 and H. What will happen? I'll just number it 1, 2, 3, 4, 5, 6, 7, 8 and 9. 9 carbons you have. We know that this carbonyl, this second is going to attach on the 9th, right? So 1, 2, 3, 4, 5, 6, 7, 8. That means 8-membered ring will be formed. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay. If I say this is my second position, right? On the first position you have, first is your, second position is double bond O. Wait a minute. Okay. So this second is attached to this CH2, right? This is alpha, right? I have to attach this second to the CH2. And to that second position, what I have to do, if I make this as second, I have to make it as OH, right? And this second position has one more substituent, that is methyl. Okay. Third, then this will be 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. Now is the 9th one. It is attached to the 9th. But 8th will have a CO group here. So here you can attach a CO group, right? You can just write it here. You can just write it here like this. You can just write it here like this. Okay. You can just write it here like this. This will be C double bond O, right? So here the answer will be this product, right? Wait a minute. One, 2, 3, 4, 5, 6, 7, 8. Oops, a big blunder I have done here. Reason being because it has 2 alpha. So sorry. It has 2 alphas, no. This is also alpha, this is also alpha. And 6-membered ring is more stable as compared to 8-membered ring. Right? 6-membered ring is more stable, 8-member is not stable. If you have the option to make 6-membered, you will make 6-membered only. Right? So here you can write it as, here this will be CO and this is CH3 only. So you can write this as CH2, this is H and then it is CO, then it is CH3. Right? 2, 3, 4, it will be H here. Right? Now, 6, this is 7, this is 8, this is 9. Now, which is alpha? This is also alpha, but it will prefer the smaller ring, right? So here this carbonyl will be attached to this carbon. That is 1, 2, 3, 4, 5, 6 carbons I need to have in my final ring. So 6 carbons I will have in my final ring. If I am assuming this to be 2, this is 3, assuming this as 2, this is 3, this is 4, this is 5, 6 and 7. Now on the second position, what you have, this will be converted to, double bond O will be converted to OH here, right? And on the second position, one you have methyl group, right? One you have methyl group, right? Then on the 7th position, right, this is having alpha hydrogen. And on the 8th position I have not written here, right? 7th position is connected to this one. 8th position I have to make here, that is CO. Then you will have one CH3. Then this is CH3. This will be formed here, right? Now students, firstly tell me, are you clear on this thing, how to form this intramolecular, right? Firstly, so I have formed this with the same method, right? With the same method, that this is attached to alpha carbons, right? 6-membered ring will be formed. On the second position, you have double bond O is converted to OH and one is methyl group that you have. On the 7th position, you have CO and CH3 that I have attached here. Now, I know from alpha and beta position, if this is my CO, this is my alpha and this is my beta position, this OH will be eliminated and from here, hydrogen will be eliminated. This double bond is shifted to this side, right? Hence, I will have the formation of, this is CO, CH3 and here it is double bond and here it is one methyl group, okay? Here it is one methyl group. Okay guys, understood this or not? Okay guys, everybody, is that clear to you or not? Is that clear or not? Everybody in the chat box. Is that clear how you had the formation of that compound? Is that clear or not? Right? Okay. Now let us talk about Cannizzaro reaction. Right? In Cannizzaro reaction, a very simple thing, that no alpha hydrogen should be there. If there is no alpha hydrogen in both the products, the answer will be Cannizzaro reaction. And here concentrated base is used. Right? Aldehyde undergoes self-oxidation reduction, disproportionation reaction. That means one is converted to alcohol, other aldehyde is converted to carboxylic acid salt. That means aldehyde to alcohol is reduction. That means in one case, a reduction is happening. When aldehyde is getting converted to carboxylic acid, that means oxidation is happening. So in the same step, with the same reactant, you are also doing the oxidation of that reactant, you are also doing the reduction of that reactant. So that is called disproportionation reaction, right? So one molecule of aldehyde is reduced to alcohol, another is oxidized to carboxylic acids. So answer is this. This is your self-Cannizzaro. In this, one molecule is converted to the same number of carbon, it is converted to alcohols. This is CH2OH. And this will be converted to carboxylic salts. That is HCONA, right? That is converted to HCONA or HCOK, right? Whatever base you have used, right? Okay. Okay guys, similarly with, if you have benzaldehyde, again benzaldehyde do not have any alpha hydrogen. So here also this CHO group is converted to CH2H and this CHO group is also converted to COONA. Right? COON. That is called the Cannizzaro reaction. Right? That is called the Cannizzaro reaction. And here, this is the mechanism of Cannizzaro reaction. When you have the molecule, right? Firstly, base, what it will do? Here, base is acting as a nucleophile. In aldol condensation, because it had alpha hydrogen, see, a simple initiation step for this is, when base which has the tendency to abstract the proton, if it sees alpha acidic proton, then it will try to take it. and hence you will proceed with the aldol condensation. But if it does not have any alpha hydrogen, it cannot abstract the proton, because this is not alpha, this is not alpha carbon, this is a carbonyl carbon, and the hydrogen attached to alpha carbon is alpha hydrogens, right? So it has no alpha hydrogen. That is why base will act as a nucleophile here. It will attack on the positive side and the electrons will jump here. It will have OH here. So sorry. This is have OH here, and this is electrons will jump here. This is O negative, right? Now again another molecule will attack here, and hence you will have the formation of this H positive will leave, double bond will shift here. This will form a carboxylic acid salt, right? Then you will have the formation of the alcohol also after the reduction. Then you will have the formation of CH3O negative, right? Okay. Because here the electrons are shifted to this side. The electrons are shifted to this side. This will be CH2O negative, right? This will be formed, right? And that H positive will attack on this side. Basically, this H positive, this is going to eliminate and attack on this side, right? And hence you will have the formation of CH3O negative. Now, what will happen? You will think that sodium phenoxide or sodium alkoxide is formed, but in reality, this hydrogen will be shifted here, and hence you will have the formation of alcohol, and Na positive will attack here, and hence you will have the formation of carboxylic salt. So that is the full mechanism here, right? Okay. Now, what about cross aldol? Now, this is a very, very important step. This is a very, very important question, right? If ma'am we talk about cross aldol condensation, then what will be the right thing to do? Then what will be the, now ma'am if you talk about cross aldol, you have two different reactants which should be converted to alcohol, which should be converted to carboxylic salts, right? For example, you had this kind of thing. This is another product, this is another product. Now the question is, should this be converted to alcohol or this be converted to alcohol? So for that we have this very simple thing. On using two type of carbonyl compounds not having alpha hydrogen, acid salt will be corresponding to that aldehyde which it will approach without any hindrance, right? Acidic salt will be less hindered, right? Why it is so? Why it is so? Because firstly, you had the formation of this acidic salt, right? The OH negative is attacking on, the OH negative is attacking and forming the acidic salt here. That is why that acidic salt will be formed which has less steric hindrance, right? Okay, because OH negative is attacking by steric hindrance factor. For example, here you have very large groups. So it will be very difficult for OH negative to attack here, right? So this is what we are saying, less sterically hindered thing will be your carboxylic salt, and the other will be the alcohol part, right? So here the answer will be less sterically hindered is this one. So this will be your carboxylic salt, that is HC double bond O, and this is Na positive here, right? And the one which is more sterically hindered is your alcohol. So this is C6H5CH2OH, CH2OH. Again on this side, this is less sterically hindered, so this will convert to carboxylic acid salt. This is more sterically hindered. This has three big groups here. That is why it will form alcohols here, right? Okay guys, this is from CH2OH. This CHO is converted to CH2OH. Tell me students, is that clear to you or not? Thank you so much, Yash. Thank you so much. Thank you so much for your appreciation. Now tell me, is that clear? This thing can be asked to you in the exam. They will give you two products and then you will be like, ma'am, two products we have, which to form alcohol, which to form carboxylic acid salt. Right? Crystal clear? JEE full mock test. I am revising right now. This is now the time for. This is the, you just 1 month away, right? So this is the like time. Now if you don't start, then when you will start mock test, right? Now next is electrophilic substitution reaction. Now for that very simple thing I'll tell you. Electrophilic substitution reaction. Basically, we are talking about the aldehydes, right? So see one thing here. Firstly, tell me one thing. You have C double bond OH, right? Is this meta or is this para or is this ortho directing? For that, you need to know one thing. If to a benzene ring, you have the attachment of a group that has lone pairs, right? Then the electrons will be shifted here, electrons will be shifted here. That means that this thing will show ortho and para position will have negative charge. Negative here, wait a minute, para negative and negative. That is why it is ortho para directing towards electrophilic substitution. Electrophilic means electrophile will substitute the hydrogen. So towards electrophilic substitution, electrophile, which is electron loving is in ortho and para position. But if you have a group like this, to this benzene ring, you have the attachment of a group which is further attached to a atom, let's say X, but X is more electronegative as compared to G. That means here electrons will jump here, the electrons will jump here. That is why further it will jump here. That is why on the meta position you will have positive charge. Wait a minute, so sorry. Yes, electrons will jump here from this side. So on the ortho position and para position you have positive side. That means towards electrophilic substitution, electron density will be more on meta position. That is why it is meta directing, right? That is why it is meta directing, right? Okay, yes. Now, tell me, this is meta or para? Carbon is connected to double bond O. Oxygen is more electronegative as compared to carbon. So definitely it will take out the electron. This is plus N, this is minus N. Definitely it is meta directing. That is why we say aldehydes are meta directing. Benzaldehyde is meta directing. It is going to give you meta directing products. Aromatic aldehydes and ketones undergo electrophilic substitution at the ring. Carbonyl act as deactivating, that means minus M effect it is showing, and a meta directing group, right? Meta directing group. Now, okay, Vanshika, great. I am so happy to know that. Now, don't worry, I'll teach you for JEE as well, right? I'm so happy to know that. Old students. So now electrophile will attack on meta position. Now you understood now why electrophile is attacking on the meta position, right? Because of the more electron density on the meta position, right? Okay, yes everybody. Now that is the thing that I was telling you, that how the resonance will happen, how it is going to eliminate the O electrons from here and electrons from here. Then will be positive charge on ortho, then para, then ortho position. That is why the electron density is more on the meta position. Hence it is meta directing towards the electrophilic substitution. Now everywhere we have already done that which nucleophile will be formed. So when you have nitrating mixture, nucleophile that will be formed is NO2 positive. As this is meta directing, so it will attack on the meta position and hence you will have meta-nitrobenzene, right? Next is when you have HNO3 and concentrated H, this so we have done only, right? No. Yes. Next is when you have acetophenone, right? Here you have COCH3. Again, this will attack on the meta position, right? Again, it will form the electrophile NO2 positive and this will attack on the meta position. And this will again attack on the meta position because this is also carbon is connected to double bond O. Oxygen is more electronegative than carbon. So it will take out the electrons and it will be deactivating and minus M effect it will show. Right? Okay guys? Yes everybody. Now I think we are left with some questions. Questions we will do in the next class, right? Because in the next class we are going to do some questions. We are going to do carboxylic acid, right? So these are the two things that we will do in the next class. Okay guys, everybody in the chat box? Yes? Okay, so everyone, bye-bye, take care, see you all in the next class and I'll text you when the next class is happening, right? That is already scheduled, right? Aldehyde, ketones and carboxylic acid part 2, but do not miss that because we are going to do a lot of previous year questions from your JEE mains and advanced. So don't even miss even a single question from that, because you never know what kind of question will be asked to you from that lecture, right? Okay, bye bye. Yes. Ma'am, I think benzene ring have a negative cloud, so it only undergo electrophilic substitution. Yes, definitely, you are absolutely right, because benzene ring has a negative electron cloud delocalization. That is why electrophile is attracted towards it. And where you have more electron density, to that position, the electrophile will attack. Right? Okay, bye-bye. Take care. See you all in the next class. And don't forget to comment down below, because I see you guys don't comment, right? When I see comments for JEE English, I don't see anything there, right? So that is very disappointing. If you like the way I teach, if you want me to teach you more on this channel, then comment down, like this video and share this with your friends, right? And spread this knowledge, right? Okay, bye-bye. Take care. See you all in the next